No finite star physically broken.
When you think about it, oh my God, so sad story in a way. And me feeling very sadly. Me feeling nobody love me. Me feeling nobody love me. Me feel like nobody love me.
An ancient world, which has existed for more than 4.5 billion years.
Nobody loves me.
Just like the other planets.
That's what it feels like. That's what it feels like.
Formed around the same time as the sun. But 4 billion years represents only a fraction of the universe's total life. And planets have almost certainly existed for longer. At the beginning of the universe, however, there were no planets. There was only hydrogen and helium gas, which went on to form stars, but not worlds.
That's the way it works.
It was only later, when the universe's gas had evolved, that planetary systems started appearing out of the dust. Knowing when the first planets formed and what they were like is a complex question with a broad range of considerations. But by studying the extrasolar planets in our galaxy, we've learned that the genesis of planets may be older and more unfamiliar than we ever could have imagined. In order to know when the first planets began forming, we first need to understand how a planet forms. We have a pretty good idea of this, thanks to scores of successful missions to study the birth of new star systems. We know that stars and their accompanying planets begin as cold clouds of unassembled gas in space, containing many different elements and compounds, but primarily hydrogen and helium. The asymmetricity of these clouds means they are always fragmenting and interacting within themselves, contracting and eventually undergoing a gravitational collapse. This compresses matter from the cloud into a small, dense and hot seed, which will grow into a new star eventually, with the gas surrounding it collecting into an oven-like incubator, which supplements the interior seed with more gas. Once the embryonic star reaches a certain mass, about 80 times that of Jupiter, it ignites a nuclear furnace and begins to shine, erupting powerful beams of energy which dispel the incubating cloud. This expelled gas then flattens into a spinning, scorching accretion disk around the star, which persists for around 10 million years. And it is at this stage in the young star's life that the race to form planets commences. All of the planets in a given star system form from material within the star's accretion disk during this 10 million year window. And once the disk is cleared, no new planets will ever be able to form around that star again. At the very start of this window, the disk will be extremely dense and far too hot for anything to form inside. But as the young star erupts jets from its photosphere, some of this material is driven away, and the temperature within the disk falls to a level at which things begin to happen. Initially, particles condense to form crystalline grains.
Hello, buddy. Glad of you to join me.
The grains to create clumps of material. Within a few 100,000 years, chunks of dust with diameters of a few centimeters will have formed, at which point they become massive enough to begin exerting an acute gravitational influence. This allows them to attract and accrete dust from their surrounding disk, increasing their mass and bringing them within range of other chunks. Within a million years ago, this process has given rise to rocks and boulders which exceed 1 kilometer in length, known as planetesimals,
Time to go ghost, dude. I'm ready.
These
How do I
chunks
look?
of rocky
Time to go
debris
ghost,
then
right?
barrel around their
I
accretion
just want to
disk,
reply to this guy
attracting
here, right?
dust and
So,
smashing
Here we
into
go. I need
other
some motivation
boulders,
this morning, so let's check it out,
building
right? So
planetary
let's start,
cores
guys.
from the ground up. The
Well,
more
it's time to go
massive a
ghost.
single object becomes, the better suited it is to gravitationally dominate its region of the disk, enabling the runaway accretion of much larger bodies at the expense of
Here we go.
smaller
I need some
ones.
motivation this morning, so let's check it
And
out, right? So
thus,
let's start this,
within
guys.
only 100,000 years of the planetesimals taking shape,
So I just want to reply
the
to this guy
majority
here,
of the
right?
system's
So,
planetary mass
here we go. I
will be
need some
shared
motivation this
among
morning,
a
so let's
few
check it out,
dozen
right? So let's start this, guys.
sub-Earth-sized, rounded rocky cores known as
Well,
planetary
it's time to go
embryos.
ghost.
If these planetary embryos lie relatively close to their parent star, then collisions will determine their ultimate fate.
Nah. I don't
Once
think
the
it's
planetary
going gas all
formation
night,
window
no way. Let's see what
closes,
this
these
is not
few dozen
planetary anyway.
embryos
What
will
is it?
collide
Now
and
what?
merge into a handful of small rocky terrestrial
So when can
planets
we begin to
like
start
Earth,
to know us more?
Venus, Mars,
When can that
and
start?
Mercury.
That's no talking again.
I'm ready to. How
Can
do
I have the last word? It's fine.
Alternatively, if a budding planetary embryo lies much further away from the parent star, then it may lie in a region where it is cold enough to sustain another kind of planetesimal chunk, composed of frozen volatile substances like methane, ammonia, and water ice instead of rock. When cold enough to assume a solid form, these substances provide abundances of extra material for planetary formation. This can lead to the rapid accumulation of massive planetary cores, weighing more than 10 times the mass of the Earth. And if this happens early enough in the planetary formation window, then the icy core will eject stray hydrogen and helium atoms from the surrounding disk before they are blown away by the host star's ejection. These light elements collect in the planet's atmosphere until they form a thick, choking, extended layer of critical point liquefied gas, known as a gas giant, like Saturn and Jupiter. These worlds can wind up being dozens of times the diameter of the Earth and hundreds of times more massive. However, not every icy planetary core that reaches this 10 Earth mass threshold will do so early enough to attract hydrogen and helium gas, as these elements will have already been largely dispersed. But the planetary core will still be able to attract a thick atmosphere of volatile ices, albeit not in as large quantities as a gas giant. And so we refer to this kind of planet as an ice giant, like Uranus and Neptune. Whatever forms during the planetary formation epoch, at the end of the window, the accretion disk will have cleared completely, having been accreted by planets or dispelled by radiation. And no new worlds will be able to form. And so, this provides a rather convenient means for astronomers to measure the age of an exoplanet. Because all natural satellites in a star system form with the primary, an accompanying planet will invariably be roughly the same age as its host, minus a few million years. And so, to know the age of an exoplanet, we simply need to know the age of the star it orbits. And to work that out, we need to know the star's metallicity. A star's metallicity is its share of elements heavier than hydrogen and helium. It's only ever a few percent at most, but this is still enough to drastically alter the chemistry and destiny of a star system. In astronomy, a metal is any element heavier than the two H's. So things like oxygen, carbon, nitrogen, and magnesium are all considered to be metals in this case. The planet's forming process we just discussed needs these metals. Without them, dust grains and planetesimal material would not be able to condense, and self-gravitating bodies would not arise. And there is only one place we know of where metals like this are synthesized, inside the cores of stars. Stars shine through the process of nuclear fusion, the crushing of light atomic nuclei to form heavier and more complex nuclei, or metals. When the first generation of stars illuminated the universe around 200 million years after it was born, there were no metals, only hydrogen and helium gas left over from the Big Bang. Thus, these early stars were made almost entirely of primordial light elements, and lived very short and turbulent lives which ended in explosive supernovae. But during their brief energy-generating cycles, they are believed to have fused the universe's first metals, converting the fuel in their cores into elements like lithium, nitrogen, argon, and ultimately iron. Then, when these stars reached the end of their lives and exploded, these metals were ejected into their surrounding gas clouds, lacing interstellar mediums of hydrogen with heavy elements, each explosion contributing to the ever-evolving chemistry of the cosmos. And then the next time these gas clouds collapsed to form new stars, metals were mixed in with the process, ultimately enabling the formation of stabler, longer-living stars with higher metallicities. Therefore, we can derive a linear relationship between a star's metal content and its age. The higher a star's metallicity, the later it must have formed, with a higher number of gas-enriching supernovae preceding it. Thus, it is a young star. Alternatively, metal-poor stars, which show a distinct lack of heavy elements, must have emerged at a time when the universe's gas was not nearly as enriched as it is today, and thus the star is probably ancient. As mentioned, metallicity would have been close to zero within the oldest generations of stars, and planetary systems wouldn't have been able to form that early on. But it seems at some point, the universe crossed a threshold at which its stars were enriched with enough metal to start grinding out planets through accretion. And so, the key to knowing when those first planets took shape lies in understanding when the cosmos was enriched to the level sufficient. In order to get a better idea of when this might have happened, scientists spent decades scouring the Milky Way galaxy to find its oldest stars and worlds.
You'll never realize how bitter and
Back then,
spiteful the
you had
average
two main
person
ways
is
of
until you start
identifying
posting on social
exoplanets,
media.
either
Since I've
by
started
spotting them
posting,
as they
I've been
pass
called
in front of
stupid,
their parent
I've been
star
called
and
ugly,
transit the
someone
light
even
source
called me
relative to the
the
Earth,
CEO of grouping
or by
gangs.
spotting the wobbles in a star's spectrum as a result of a companion object acting on it.
You tell me, mate.
Both methods,
Yeah, I was
however,
gonna
are
picture
prone
it.
to biases, which impeded our
Don't
early
hear about it
perceptions of the
I
Milky
don't even
Way's
get it, mate. I
planetary
don't even
population.
understand me, mate.
Both
Yeah.
means
Can we
favour the
don't have it or something?
detection
I don't
of
know.
very large Jupiter-sized worlds orbiting
Yeah, I
close
don't
to
know
their
that.
parent
But I
stars.
didn't realise, mate. I didn't know fucking
This type of planet is known as a hot Jupiter. They are gas giants which have migrated inwards through their system as they have accreted material, winding up very close to the parent star indeed,
Sometimes, yeah.
where they exert the most detectable wobble and
Okay.
transit most regularly. Improving
Are you not going to say hello, Mr. Watcher? Are you not going to say hello?
as such,
Or are you just going to keep on edging?
Jupiters that revealed themselves
You're just going to keep on edging?
frequently
Or are you going to say hello?
earliest, least
Huh?
sensitive exoplanetary
Are you
stars
edging right
in the
now?
mid-1990s,
You better not be, babe.
leading us to
That's
believe
naughty.
that they were the prevailing type of world,
Blatantly edging, you know it.
and a good indicator of the types of stars that can support planets.
Just so you know, I'm the boss and you're not the boss.
Hot Jupiters prefer higher metallicity star systems with
Absolute
large
disgusting
amounts of
people.
dust.
So stupid.
In order to get to
So
this stage,
stupid.
a gas giant needs to accrete vast amounts of rocky and volatile material, which there simply wouldn't have been enough of in early metal-poor star systems. Thus, we only really find core accretion gas giants like Jupiter in systems with high metallicities. And because they accounted for the majority of known exoplanets back then, this led us to incorrectly conclude that planetary systems need sun-like levels of metallicity to exist, and that space subsequently wouldn't have been enriched to the level sufficient until about 6 or 7 billion years after the Big Bang, just under half the universe's present age. That is a long time without any planets, and it would have damning implications on the probability of alien life elsewhere in the cosmos. But moving into the 21st century, we began to realise that this wasn't the case. Thanks to technologically superior observatories like Hubble, Spitzer and Kepler, transit surveys and wobble detections became the work of computers, capable of tracking thousands of stars at once to identify even the most discrete signs of satellites. Today, we've identified over 5,000 exoplanets in an array of different sizes and types, with some boasting ages of more than 10 billion years.
I just find it weird.
And among the oldest and most jaw-dropping of these worlds is the hellish planet Methuselah.
Nah.
Hello, my friend. So now we're going to try. So now, time for the food review of my wonderful.
Methuselah is, to date, the oldest planet we've ever discovered, appropriately named after a biblical patriarch who was claimed in the book of Genesis to have lived for just under 1,000 years. His namesake planet lies around 7,200 light years away from Earth, in the constellation of Scorpius, near the heart of the ancient globular star cluster Messier 4. For a long time, it was thought that the stars within globular clusters would not be capable of hosting planetary systems. The lack of metals, the contrasting tidal gravitational influence, and strong tailwind emissions produced by these tightly packed stars was expected to dispel protoplanetary disks before they had a chance to condense, rendering planetary formation impossible. As such, we never thought we would find a planet inside one of these old, inhospitable star clusters, and our early observations of globular clusters seemed to back this up, when we failed to detect any evidence of hot Jupiters lying within. But in M4, the story is different. In 2003, the Hubble telescope identified several metal-core helium white dwarf stars, with estimated ages of around 13 billion years, making them among the very oldest stars we've ever discovered. And loosely bound to one of them, in spite of the harsh stellar nature, is the planet Methuselah. Its discovery represented a number of record-breaking firsts in the field of planetary science. In addition to being the oldest planet we've ever found, it was also the farthest that had been discovered at the time, and the first inside a globular cluster. And it was even the first circumbinary exoplanet ever discovered, orbiting not one but two burned out post-plane sequence stars near the core of the cluster. One of the special binary elements is the aforementioned ancient white dwarf. The exposed core of a dead star too small to go supernova. The other component is a neutron star, the core of a dead star that was large enough to go supernova, leaving behind an ultra-compressed, irradiating, city-sized sphere of neutron-degenerate matter. And it was through this object that we were able to discover Methuselah. PSR B16 2026 is a pulsar, meaning the neutron star emits beams of radiation from its polar axes as it rotates, which periodically fall in the direction of Earth, where they are detectable as a series of precisely timed lighthouse-like pulses. This allowed us to identify the system in 1988, and in the years since, we have managed to identify gravitational companions thanks to the wobbles they cause in the pulsar spectrum. Almost straight away, astronomers inferred the presence of a second body in the system thanks to the obvious effect it had on the signal. But throughout the 1990s, the possibility of a third
You can identify yourself,
beyond the binary
you blatant loser.
was also
You're going to sit there and watch me like a goon.
to be either a
You've got no life.
or perhaps a particularly massive planet. By
And you're a
2003, the latter hypothesis was all but confirmed when NASA used Hubble to identify the white dwarf in the system, and from that deduce an accompanying planetary mass body, around 2.5 times more massive than Jupiter. That body is the planet Methuselah, an ancient visitor to this most torrid of star systems, orbiting well adrift of the chaos at a distance of 23 astronomical units. Given the planet's wide orbit and hostile neighborhood, it is improbable that Methuselah is a true satellite.
You think I don't know you're watching me, you goon?
Rather, it is thought that the planet formed further out in M4.
You're disgusting.
Around a solitary star with a dusty disk, before gravitational disturbances knocked it out of its neighborhood and sent it hurtling towards the core of the cluster. Then it became entangled in the grip of this colossal tug of war between ghost stars, where it remains orbiting to this day, completing a full lap of the system once every century.
So I just want to reply to this guy here.
However, assuming the planet formed somewhere within M4, then it is probably around the same age as the rest of the cluster, whose 100,000 constituent stars were born together rapidly in the early universe. This gives Methuselah a truly staggering estimated age of some 12.7 billion years, little under 3 times the age of Earth, completely uprooting our long-held perception that planets need metal-rich stars to exist. The most intriguing thing about this planet's existence is that it is a gas giant, and not just any gas giant, one more than 2.5 times the mass of Jupiter. Even if we had expected to see planets in such ancient, low metallicity star systems, we would have expected very small, immature rocky worlds, ground out from the scraps of metallic gas that would have been available at the time. Yet Methuselah not only managed to form in this most simplistic of chemistries, but somehow managed to accrue more mass than the entirety of the solar system's planets. At this early stage in the universe's life, Methuselah certainly wouldn't have reached this size via core accretion, the process we discussed at the beginning, where rocky planetary embryos reach 10 Earth masses and attract a gaseous atmosphere. That process requires a substantial quantity of metals, the likes of which there just wouldn't have been in this ancient globular cluster. And so, this suggests that Methuselah may have formed via another planetary formation mechanism, one which relies far less on metals and thus has enabled their existence throughout the duration of the universe's life. We now believe that, in the very oldest star systems, born with high fractions of hydrogen and helium gas, planetesimal coagulation may not have been necessary to form giant planets. Instead, gravitational instabilities within these dense primordial disks would have resulted in the contraction of clumps of light gas into self-gravitating bodies. If one such clump became sufficiently massive and compact, then dust grains would have condensed inside the object, from the trace quantities of metal elements present in the planet-forming disk. These dust grains would have then sunk towards the center of the body and formed a makeshift planetary core allowing the clump to begin acting as its own planet. This new world would have then swept round its young stellar disk, clearing vast trails in the system's hydrogen and helium gas, forming a massive, dense atmosphere and ultimately becoming its own type of heavy-duty gas giant, made mostly of light elements. Therefore, even in the absence of essential core-accreting materials, gas giants like Methuselah, which formed in this manner, would have been able to dominate their planetary systems to attain super-Jupiter sizes, even in the most metal-poor environments. This type of gas giant may well have been incredibly rare in the early universe, as the prevalence of gas giants is exponentially tied to rates of metallicity. But the existence of Methuselah alone shows us that the formation of planets was clearly underway within only 1 billion years of the Big Bang. And so, if gas giants have been able to form for the longest time, then what about terrestrial planets? When did the first landscapes appear to overlook the young universe? As we mentioned, the process of rocky core accretion builds from the ground up. And so hypothetically, this should have enabled the formation of small terrestrial planets long before it could give rise to larger ones. These planets would have required at least some level of metals, and so may have taken a bit longer to emerge than primordial gas giants like Methuselah. But even so, it does seem like terrestrials have been forming, in this galaxy at least, for well over 10 billion years, with their existence seeming to be much more indiscriminate when it comes to metallicity. We've uncovered hundreds of these rocky exoplanets in the Milky Way, around stars of varying ages. Among the oldest are those worlds residing in the Kepler 444 system, an ancient triple star system lying 119 light years away from the Earth. The system's primary body is a low-mass orange dwarf star, which is home to no less than 5 terrestrial exoplanets. They range in sizes from Mercury to Venus, and all have settled, stable orbits, implying that there are no gas giants on the inner part of the system. Unfortunately, none of these rocky worlds are thought to be habitable. They all orbit closer to their parent star than Mercury to the Sun, rendering their surfaces scorched and lifeless. But with an estimated age of more than 11.2 billion years, these worlds show us that the framework for rocky terrestrial planets has been in place for almost as long as that of gas giants, and that both types of world have been able to form throughout the majority of the universe's life, their emergence far less reliant on metals than we once realized. With all these things considered, we can conclude that the planetary formation mechanism, whichever form it may take, is robust and resilient, able to manifest in a wide variety of circumstances, even in the absence of high metallicities. As such, planets are very likely to be abundant throughout the universe, with each galaxy housing hundreds of billions of every possible type and age. And so, the inevitable follow-on question is, if terrestrial planets have existed for most of cosmic time, then how soon after their emergence did they become capable of supporting life? If the universe's terrestrial worlds have had more than 10 billion years to find balance, then it fundamentally increases the probability of other sources of life elsewhere in space. But of course, habitable worlds require a much more precise and refined set of circumstances than your average lifeless terrestrial. To make a rocky world livable, you need all sorts of complex ingredients, temperate atmospheres, chemical compounds, energy gradients, and above all, a flowing liquid solvent for mixing molecules and facilitating life-giving chemical reactions. On Earth, that solvent is water, which has flowed in a liquid form on the planet's surface for billions of years. However, there are a number of other substances, such as ammonia, which possess the hydrogen bonding properties necessary for biochemistry when in a liquid form. And thus, we can envision a wide variety of...
Are you two fucking sitting here wanking each other off? What are you doing? Just sitting there.
The key thing that all these recipes
Fucking
need,
goons.
however, is time. Balanced, temperate conditions need to remain largely undisturbed for hundreds of millions of years, or perhaps even longer, to allow enough time for the unknowably complex chain reactions of abiogenesis to proceed. This effectively rules out the universe's first populations of stars from discussions surrounding habitability. In addition to lacking sufficient quantities of chemical compounds, these early stars would have not lived anywhere near long enough to sustain the formation of planetary systems. Galaxies would have also been flooded with stellar wind, supernova shockwaves, and cosmic rays, strong enough to snuff out any budding biosphere. But once the stubbornly high star formation rates that characterized the early universe had died down, galaxies would have almost certainly started to bear habitable rocky planets after a few billion years. Whether any of these worlds ultimately resulted in habitation depends on the number of opportunities there have been for life to emerge. For a long time, astronomers believed that the galactic habitable zone, the postulated belt of the Milky Way with the right balance of stability and metallicity to enable habitability, would make up only a very small part of its total expanse. Galaxies like the Milky Way tend to evolve chemically from the inside out, with the majority of metal-infusing supernovae occurring within the crowded galactic core, resulting in centralized higher metallicities. In contrast, further away from the galactic nucleus, stars become more spread out, and subsequently lie in the paths of fewer supernovae, constraining their access to metals. Therefore, it was once believed that the outskirts of the Milky Way and all spiral galaxies would be badlands, almost entirely devoid of planets altogether, let alone habitable ones. This considerably reduced our estimate of the number of potential opportunities for life by excluding hundreds of billions of potential star systems from consideration. But in recent years, we've seen evidence that planets were indeed forming in metal-poor environments. The question is, how did such large areas of the galaxy come to be enriched to the level needed for planetary systems so early on? Scientists have probed the depths of the universe in an attempt to determine the metallicity of the oldest galaxies by using the background light of quasars as an illuminator for taking spectral measurements. What they found was that sun-like levels of metallicity could be found in galaxies all the way out to redshift 10, little under 13 billion years ago. Finding metals inside these oldest galaxies isn't wholly surprising on its own. After all, star formation rates would have been at their highest during this era, resulting in vastly enhanced rates of metal-generating supernovae. But this early on in the evolution of the cosmos, barely a billion years after it was born, you would expect the scarce number of newly synthesized metals to occupy only a relatively small region near the crowded galactic core. where the bulk of stellar enrichment would have been occurring. But instead, scientists were stunned to find traces of metals in primordial galaxies as far out as 50,000 light years from their respective galaxy cores. Even this early in the universe's life, the few metals that had been produced were still finding their way across the entire expanse of their host galaxies. The most probable reason for this breakneck spread is the radiation from a starburst event, which gave freshly created metals in the heart of the galaxy a lift into the outer rims. Back then, bustling colonies of newly formed stars would have emitted so much stellar radiation that any metals released by supernovae would have been forced outwards by radiation pressure, pushing them as far out as to seed even the more remote metal poor star systems with new heavy elements. At the time, the high volumes of stellar radiation would have rendered these young galaxies uninhabitable. But once the starburst events ended, they left behind enormous swathes of enriched gas all over their host galaxies. This could have resulted in an explosion of worlds with habitable properties throughout galaxies right across the universe, just as soon as the conditions became right for their emergence. And with the groundwork for livable planets laid across such vast areas so early on, it makes it ever the more likely that one of these worlds would have clicked into an awakening of life independent of our own. Unfortunately, until we find solid, indisputable evidence of that somewhere else in space, we can never say for certain that any quantity of habitable worlds is enough. Even if the galaxy is brimming with temperate water worlds and Earth analogues, life may be so complex that even the estimated 100 billion planets of the Milky Way galaxy are not sufficient for more than one inhabited world. But in any case, and even if the galaxy is completely lifeless besides Earth, the sheer number of rich, complex and temperate worlds that have managed to emerge out of the chaos of the early cosmos, it's nothing short of a miracle. Just think of the fascinating stories that may have played out on some of these worlds over 12 billion years.
Every science fiction empire gets it wrong. Every galactic civilization sprawling across the stars in movies and novels violates the same laws of physics that no intelligence, no matter how advanced, can override. The Milky Way contains up to 400 billion stars spread across 100,000 light years of space. Colonizing even the nearest one would require energy budgets exceeding everything humanity has produced in its entire history. Scaling that effort to a second star doubles the problem. A 10th star does not multiply it by 10, it multiplies it by thousands. The galaxy is not just large, it is a physics engine designed to prevent coherent control. Distance, time, energy, and entropy conspire together to guarantee one outcome. Isolation always wins. If you enjoy having your assumptions about the future of civilization completely dismantled by the cold hard math of the universe, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep bringing you these explorations into the science that shapes everything. Now, make yourself comfortable. Let's begin. The Milky Way is not what you think it is. When most people picture our galaxy, they imagine a neat spiral drawn on a classroom poster. A flat disk of stars arranged in elegant arms curving outward from a bright center. That image is useful for introductory astronomy courses. It is catastrophically misleading for understanding why no civilization could ever spread across this structure. The real Milky Way is a three-dimensional monster of almost incomprehensible proportions. It spans approximately 100,000 light-years from edge to edge across its visible disk. That disk measures roughly 2,000 light-years thick in the outer spiral arm regions and swells to nearly 12,000 light-years near the dense central bulge. But the galaxy does not end where the visible stars thin out. An enormous halo of dark matter, ancient globular clusters, and scattered relic stellar populations extends far beyond the bright disk in every direction. Recent measurements place the full extent of the galactic halo at over 200,000 light-years in diameter. Some estimates push even further. This is not a flat shape you can cross by drawing a straight line from one side to the other. It is a vast, three-dimensional volume of space filled with structure, mass, gravitational complexity, and above all else, terrifying emptiness between the points of light. Start with the numbers that matter most. The Milky Way contains somewhere between 100 billion and 400 billion stars. That range itself reveals something important. We cannot even count the stars in our own galaxy with confidence. The uncertainty spans a factor of 4. Thick dust clouds strewn across the galactic plane block visible light from reaching our telescopes across the full breadth of the disk. Entire stellar populations hide behind curtains of molecular gas and interstellar debris that are opaque to optical instruments. Infrared surveys and radio telescope mapping campaigns have revealed enormous numbers of stars in regions that visible light surveys completely missed. The galaxy is so large and so structurally complex that simply cataloguing its stellar population remains an active and incomplete project after more than a century of modern observational astronomy. Yet even the conservative lower bound of 100 billion stars creates a number that overwhelms human cognition. If you counted one star per second without ever stopping to eat, sleep, or pause for breath, you would need more than 3,100 years to finish the count. That is longer than the entire span of time separating the present day from ancient Egypt. If you instead needed to count the upper estimate of 400 billion stars at that same pace, you would need roughly 12,700 years. Longer than recorded human civilization has existed, and each one of those hundreds of billions of stars occupies its own region of space, separated from its nearest stellar neighbors by distances measured not in miles or kilometers, but in light years. Here is where the true scale of the arena begins to bite. The average distance between neighboring stars in the solar neighborhood, the relatively well-mapped region surrounding our own sun, is approximately 4 to 5 light years. One single light year equals roughly 5.88 trillion miles. So the typical gap separating one star from the next in our local region of the galaxy stretches to at least 24 trillion miles. This is not the empty space between adjacent cities on a highway. This is not the ocean separating two continents that ships can cross in weeks. This is a void so vast and so barren that nothing humanity has ever constructed could traverse it within a single human lifetime, using any technology currently available or plausibly foreseeable. The Voyager 1 spacecraft, currently the most distant human-made object from Earth, has been traveling outward through space for more than 4.5 decades. In all that time, it has covered roughly 15 billion miles. That sounds impressive until you measure it against the interstellar gap. At Voyager's current velocity, reaching the nearest star system, Alpha Centauri, sitting just 1.24 light-years away, would take over 70,000 years. And Alpha Centauri is our closest stellar neighbor. It is the shortest possible crossing in our entire galactic neighborhood. Every other destination is farther. Most destinations are dramatically farther. But the solar neighborhood is relatively crowded compared to large stretches of the galactic average. The Sun happens to sit within the Orion Spur, a minor spiral arm structure nestled between the larger Perseus and Sagittarius arms. In this region, stars cluster with moderate density. Move toward the outer edges of the galactic disk, where stellar populations thin out considerably. Gaps between neighboring stars can stretch to 10, 15, 20, or even 30 light years. Move away from the disk entirely into the galactic halo, and individual ancient stars float in perfect isolation, separated from one another by hundreds of light years of functionally empty vacuum. The galaxy is not a uniform field of stars sprinkled evenly like seeds across a garden bed. It is a landscape defined by extreme density variation. The central bulge, a massive spheroidal concentration of red stars surrounding the galactic core, packs stellar populations so tightly that the night sky of a hypothetical planet there reflects thousands of individually visible suns. The outermost spiral arms scatter stars so thinly that a civilization living on Earth cannot gaze upon fewer nearby stellar neighbors than we. Any serious plan to spread across this galaxy must contend with this density gradient at every stage. Expansion does not proceed through a smooth, uniform medium of ink spreading evenly through still water. It must navigate alternating regions of empty and vast stretches of stellar nothing, adapting its strategy to local conditions that vary by factors of hundreds or thousands depending on position within the galactic structure. Consider what this means in terms of raw volume. The Milky Way is not a line to be crossed. It is a space. If you model just the visible disk as a single cylinder, 100,000 light years in diameter, 2,000 light years thick, the enclosed volume works out to approximately 15.7 trillion years. But that cylinder is a dramatic simulation. The real disk is warped alongside. It flares vertically in all skirts. The central bulge adds substantial volume both above and below the galactic midplane. The stellar halo is spherically well beyond the disk's edge in every direction. A more physically realistic estimate of the galactic volume, including the halo region, globular clusters and relic stars orbit, reaches comfortably into the trillions of years. Filling this volume with any kind of communication relays, colony habitats, energy collectors, monitoring probes, or supply depots requires confronting a spatial challenge that does not behave the way most people expect. Double the radius of your expansion sphere, and you do not merely double the volume you must service, increase it by a factor of 8. Triple your expansion radius, and the volume grows 27-fold. Expand your reach 10-fold, and the volume explodes by a factor of 1,000. This is the key problem inherent to three-dimensional space. It haunts every model of galactic expansion. The galaxy does not merely grow harder to push outward, it grows harder to fill, harder to monitor, harder to supply, harder to connect. Every additional light year adds disproportionately more volume, more space, more gaps, and more logistical burden than the light year. This brings us to a critical distinction that most popular discussions of galactic civilization completely ignore, collapse, or conflate. There are three fundamental categories of activity that people mean when we talk about spreading across the galaxy. Treating interchangeable is one of the most common and most destructive about the future of intelligent life. The first category is exploration. A robotic craft, a laser signal, a flyby mission to another star system. Exploration is the simplest form of interstellar activity. It requires reaching a destination, gathering data, and potentially transmitting that data back to the origin. It does not require staying at the destination. It does not require building permanent infrastructure. It does not require building a living population at the target star. Exploration is essentially a one-directional energy expenditure with no potential for long-term maintenance. Humanity has already performed versions of this within our own star. The Voyager missions, the supply of Pluto, and various Mars missions all represent exploration at interplanetary scale. Scaling this to interstellar distances is difficult, it represents the most plausibly achievable category. A sufficiently advanced civilization could conceivably send robotic probes to nearby stars or centuries of flight time, depending on the propulsion technology employed. The essential is nearby. Dispatching a Centauri at 4.24 light years is a different challenge than sending one to a star 4 light years away on the opposite side of the galactic core. Massive dust clouds and intense radiation. The second category is settlement. Sustaining colony in another star system, independently without ongoing support from the settlement requires everything that plus the capacity to transport a genetic population, comprehensive life support, construction equipment, or the means of local resources upon arrival. Infrastructure or equivalent food production technology, independent energy generation systems, medical facilities, educational institutions, governance structures, and enough stored knowledge to rebuild critical technologies from scratch if any component fails. Settlement is not a mission, it is the creation of an entirely new self-sufficient civilization from nothing, and an environment without none of the geological, biological, or industrial support systems the colonists depended upon. Every single resource must either be carried from the point of origin at staggering mass and energy cost, or extracted from whatever raw materials the destination system happens to provide. If the destination star system lacks suitable rocky planets with accessible water, if it lacks mineable asteroid belts with useful mineral compositions, if it lacks sufficient energy flux at habitable distances, the colony fails regardless of how technologically sophisticated the colonists may be. Settlement multiplies the complexity of exploration by orders of magnitude. It is the difference between sailing a boat to an uninhabited island and building a fully functional, self-perpetuating nation on that island, with no supply ships ever returning. The third category is empire, maintaining coordinated control, communication, resource exchange, governance, economic integration, and cultural coherence across multiple star systems simultaneously. This is what science fiction invariably portrays when it depicts galactic federations, interstellar republics, trading leagues, or galaxy-spanning imperial dominions. Empire requires everything that settlement requires at every single node in the network, plus the ability to exchange information, resources, personnel, and governing authority between nodes on timescales fast enough to allow coordinated collective decision-making. It requires that the civilization at Star System A can meaningfully observe, respond to, and influence events at Star System B before those events become strategically or logistically irrelevant. It demands shared technological standards, compatible communication protocols, synchronized supply logistics, dispute resolution mechanisms, and a connective infrastructure linking every active node to every other active node in the network. Empire is not merely a larger version of settlement. It is a categorically different class of problem. Settlement asks whether you can survive at another star. Empire asks whether 1,000 independent settlements spread across 10,000 light years of space can function and persist as a single coherent entity. The answer to the first question might conceivably be yes, given sufficient technology and resources. The answer to the second is where physics itself steps in and says no. Most popular discussions skip directly to empire without acknowledging these distinctions. They assume, often implicitly, that reaching one star leads naturally to reaching the next, which leads to the next after that, which eventually cascades into full galactic colonization, as if it were an inevitable chain reaction. This assumption contains a hidden error so fundamental that the entire optimistic argument collapses the moment you identify it. The error is the assumption that expansion scales linearly, that each additional star system added to your growing network costs roughly the same in energy, time, and resources as the one before it. In physical reality, expansion costs scale geometrically and then exponentially. As the volume of space your network must service grows with the length of your expansion radius, while the coordination infrastructure required to maintain coherence across that volume grows even faster than the volume itself. Reaching Alpha Centauri at 4.24 light years involves crossing a single interstellar gap between two neutron stars in one of the denser parts of the local galactic environment. The energy, time, and resources required for this one crossing are enormous, potentially in reach for a civilization substantially more advanced than our own. Now consider what happens when you attempt to expand out from Alpha Centauri to additional neighboring systems. The next nearest stars, Barnard's star, approximately 6 light years from the Sun, Wolf 359, at roughly 7.9 light years, Lalland 21 light years, 85 at about 8.3 light years, all sit at comparable distances. Each crossing to each new system demands a separate voyage with its own propulsion energy budget, its own fleet of vessels, its own colonization payload, its own decades or centuries of transit time. Reaching 10 nearby star systems might require 10 expeditions, each nearly as expensive as the first crossing to Alpha Centauri. But this exclusive local neighborhood represents the easiest possible scenario imaginable. Stars within 20 light years of the Sun are relatively close to standards. Push outward beyond this local boundary, and the terrain changes dramatically. Try to expand along the length of a spiral arm, and you must cross not just individual gaps between stellar neighbors, but navigate through large void regions where stellar density are significant factors. Try to push inward toward the galactic center, and you encounter zones of intense radiation, extreme gravitational forces, and stellar densities so high that orbiting make long-term habitation far more complex. Try to cross laterally from one spiral arm to another, you must traverse thousands of light years into the empty interarm space, where stars are staging points for resupply simply do not exist. The galaxy is not a smooth, uniform highway stretching conveniently from departure point to destination. It is a rugged and wildly varied of obstacles, voids, radiation hazards, and density extremes that renders every expansion route uniquely difficult and every additional light would reach harder than the last. Let us quantify what the galactic empire actually demands in concrete. Suppose a civilization aims to establish a coordinated presence along just one major spiral arm. The Perseus arm, which is the nearest major arm outside of position in the Orion spur, stretches approximately 30,000 light years in length. It contains billions of individual star systems. A network covering the modest corridor of this arm, say, outposts positioned at regular intervals with 1,000 light years wide and 30,000 light years, would encompass a spatial volume of 23 billion cubic light years. The total number of star systems falling within that corridor likely exceeds several billion. Every single outpost requires energy generation, communication links to neighboring networks, supply infrastructure to maintain itself, sufficient autonomy to survive the centuries or millennia of cycles in meaningful contact with the rest of the network. This is just one arm. The Milky Way has 4 major spiral arms: Scutum Centaurus, Sagittarius, Perseus, and the Outer Rim, plus several minor spurs, branches, and bridge structures. Covering the entire galactic disk would require replicating infrastructure across every arm, every interarm, a massive central bulge, and the sparse alterations. The total number of star systems that would be in to a truly galactic civilization reaches currently into the hundreds of billions. The logistical requirements do not merely add up as you expand. They compound and multiply. Each new region incorporated creates new communication pathways that must be maintained, new supply chains that must be reliably established across interstellar distances, new conditions that must be sustained in environments that are dramatically from anything the founding civilization existed. The operational complexity is not at the same rate as the territory. It grows substantially faster. This is the scale of intelligence that drives everything that follows. The argument of this episode is not that interstellar travel is impossible. It may very well prove achievable for civilizations significantly more advanced than humanity. The argument is that scaling interstellar travel from a single crossing to a million crossings introduces physical constraints that no amount of technological achievement can eliminate, because they are not engineering limitations. They are features of the universe itself. You cannot engineer around the speed of light. You cannot manufacture and fuel a million simultaneous colonization. You cannot maintain meaningful coordination in so vast that a signal dispatched from one edge to the opposite edge for 100,000 years. Problems awaiting clever solutions. There are physical boundaries imposed by the geometry of space, the finite speed of information, and the dynamic cost of maintaining order across these distances. One final dimension is attention before we move forward: time. The Milky Way is not a static target waiting to colonized. It rotates. The Sun takes approximately 230 million years in a single orbit around the galactic center. Stars at different radial distances from the core orbit at different velocities. This differential rotation represents spatial relationships between star systems. They change continuously. The stars sitting 30 light years from your colony today occupy a completely different position relative to you after a few years of galactic rotation. The survey map that your civilization drew at the start of its exploration program becomes increasingly inaccurate at the passing epoch. Routes that were optimal at launch become suboptimal or even impassable as the underlying star geography shifts beneath you. This rotation creates a compounding navigational problem for any selection effort. A chain of outposts strung along a small experience gradual distortion over time. The stars on the inner edge of the chain orbit the galactic faster than stars on the outer edge. Over millions of years, and galactic necessarily requires operations spanning. This shearing stretches, warps, and ultimately disrupts fixed network geometries. Maintaining distance between colonies demands constant corrections to account for stellar drift. And the corrections themselves require information about where stars have moved. Information that travels at light speed across gaps measured in light, arriving with inherent delays baked into the. You are not building infrastructure on solid ground. You are laying foundations on a slowly rotating platform where every point moves. This is the arena, 100,000 light years across, hundreds of billions of stars, trillions of cubic light, density variations spanning orders of magnitude, interstellar gaps measured in trillions of miles, a structure that rotates shearing any fixed network is shorter than the expansion itself would require. Three categorically distinct challenges: exploration, settlement, and empire, each exponentially harder than the last. The hardest one qualifying as true galactic civilization. Perhaps the sheer scale alone can settle the question. Maybe a sufficiently determined and patient civilization can simply accept the vastness, accept the time required, accept the volume, and push through by sheer persistence and brute force engineering. What comes next dismantles that hope by confronting the hardest wall in physics. The speed of light is not a speed limit waiting to be broken by a better engine. It is a structural feature of space-time itself that dictates exactly how much energy every journey costs, exactly how much time every crossing consumes, and exactly why relativistic travel creates temporal paradoxes that shatter civilizational continuity across interstellar distances. Nothing in the universe moves faster than light. This is not a technological limitation awaiting a breakthrough. It is not an engineering barrier that a sufficiently advanced civilization would overcome with better materials, cleverer design, or more funding. The speed of light, 299,700 kilometers per second, or approximately 106,000 miles per second, is a structural property of space-time itself. It emerges directly from the fundamental equations of special relativity, which have been confirmed by more than a century of rigorous experimental verification to extraordinary levels of precision. Every particle design is ever constructed, every satellite navigation system calibrated, every atomic clock is synchronized aboard aircraft and spacecraft confirms the identical result. The speed of light is the absolute ceiling on how fast information can propagate through the vacuum of space. Known physics provides a mechanism to exceed it. No speculative physics consistent with observed experimental reality offers a credible workaround. A single constraint, more than any other factor, determines why galactic expansion collapses into its own ambition before it even begins. What this speed limit means for travel times across the galactic is already measured. The Milky Way's visible disk stretches approximately 100,000 light years from edge to edge. But the speed of light itself, the absolute fastest that the universe can travel, crossing the full diameter of the galaxy requires 100,000 years. That number alone should give serious pause to anyone entertaining galactic empires. Light, the fastest emitted by the laws of physics, needs a span of roughly 500 generations merely to traverse a single mid-sized spiral galaxy. No physical spacecraft constructed from matter of light. The equations of special relativity with mathematical certainty. Any object possessing mass to light speed infinite energy. Not impractical that be achieved with better technology. Infinite energy. An amount that cannot be generated by any process in any finite universe. Light is not a wall you can eventually punch through. It is an asymptote. The fundamental structure of reality prevents any massive object from reaching. So realistic interstellar travel must occur at some fraction of light speed. The question becomes what fraction is achievable. What the resulting journey times look like when applied to galactic. This is where optimism begins its slow, progress. At 10% of the speed of light, the velocity of roughly 30,000 kilometers per second, approximately 67 million miles per hour, crossing the full 100,000 light-year diameter of the galaxy would require 1 million years. To anchor that number in something, consider that 1 million years ago, the species had not yet appeared on Earth. Our predecessor species, Homo erectus, was still the dominant hominid on the planet. Modern language, art, tool-making, agriculture, civilization, none of it existed. A civilization that launched a galactic crossing mission at 10% of light speed would need to sustain that mission continuously for a duration exceeding the entire evolutionary history of anatomically modern humans. 10% of light speed is an extraordinarily ambitious target. No human technology can come close to achieving it. The fastest spacecraft built by human hands, the Parker Solar Probe, reached speeds of approximately 600,000 kilometers per hour during its closest approach. 10% of light speed is roughly 1 million kilometers per hour. That is 70 times faster than the fastest object humanity has ever built. The gap between 1 and 10% of light speed is not infinite. It is a chasm spanning multiple orders of magnitude. At 1% of the speed of light, roughly 3 times per second, the galactic crossing is 1 million years. This velocity is closer to what some genuinely proposed concepts might theoretically achieve assumptions, though even this remains far beyond future engineering capability. 10 million years ago, the evolutionary lineage that would eventually produce modern humans had not yet diverged from the lineage of chimpanzees. The entire arc of human evolution, from the earliest bipedal apes through every species of Australia, every variant of Homo, every ice age migration, every civilization that has ever risen and fallen on Earth fits comfortably within the transit time of a single galactic crossing at 1% of light speed. 1/10 of 1% of light speed, 300 kilometers per second, a velocity roughly comparable to the fastest performance achievable by advanced ion drives or theoretical nuclear pulse propulsion concepts like Project Orion. The crossing time inflates to 100 million years. When such a hypothetical mission launched, the dinosaurs would have already been extinct for 35 million years, but the mammals that replaced them would not yet have diversified into most of their modern forms. The entire Cenozoic era, the age of mammals, the epoch that produced elephants, whales, primates, and eventually humans, fits inside this single transit window. These numbers do not merely challenge models of galactic expansion, they annihilate them. Any model that relies on physically transporting ships, crews, or colonization infrastructure across the full breadth of the galaxy requires timescales that exceed the lifespan of any known biological species by enormous margins. They exceed the duration of any known civilization and structure by even larger margins. And they almost certainly exceed the functional lifetime of any technological system that must maintain integrity against cumulative radiation, micrometeorite bombardment, material lubricant degradation, electronic component failure, and the slow but relentless accumulation of entropy over millions of years of continuous operation in the harsh vacuum of interstellar space. This point deserves closer examination because it is routinely considered in optimistic models of interstellar travel. The assumption is that if you solve propulsion, you solve the journey. But propulsion only determines whether the ship can move. Survivability determines whether anything functional arrives at the destination. Interstellar space is not a benign medium. It is a relentless degradation environment that attacks every spacecraft through multiple simultaneous mechanisms operating continuously over the entire duration. Cosmic radiation represents a massive threat. High-energy particles, protons and helium nuclei stripped from stellar atmosphere and accelerated to near-light speeds by supernovas and magnetic field interactions, in space at a flux density of roughly 2 to 4 particles per square centimeter per second. Each individual particle carries enough energy to penetrate centimeters of radiation and displace atoms within structures. Over decades, this causes cumulative lattice damage, brittlement in polymers, degradation in electronic systems, and gradual optical surfaces. Radiation can extend component lifetimes by factors of 100, but no known material is cumulative radiation damage over timescales of centuries. Electronic systems are particularly vulnerable. A single high-energy cosmic ray striking a microprocessor can cause bit flips, logic errors, or permanent transistor damage. Over centuries of continuous exposure, heavily shielded computing systems accumulate sufficient damage to degrade reliability below functional thresholds. Micrometeorite erosion operates on a different timescale with equally corrosive effect. Interstellar space contains a sparse but non-zero population of dust ranging from submicrometer particles to fragments several kilometers across. At interstellar cruise velocities, even a modest 1% of light speed, which is 3,000 kilometers per second, the kinetic energy of impact, with even a milligram dust grain, equals roughly 1 kilogram of TNT equivalent. Over centuries of transit through the interstellar medium, the cumulative effect of countless microscopic impacts erodes external surfaces, pits thermal shielding, degrades reflective coatings, and gradually compromises hull integrity. A spacecraft that launched with pristine external surfaces arrives at its destination, scarred, pitted, and structurally weakened by millions of individual micro-impacts accumulated over the journey duration. Material fatigue compounds these external threats with internal degradation. Metals subjected to continuous thermal cycling as spacecraft surfaces rotate between solar-facing and space-facing orientations, or as internal systems generate and dissipate heat, develop microscopic fractures that propagate over time. Seals and gaskets made from elastomers lose flexibility and develop cracks as polymer chains break down under radiation exposure and thermal stress. Lubricants in mechanical systems evaporate, decompose, or polymerize into useless residues over centuries, causing bearing surfaces to wear and mechanisms to seize. Adhesives degrade, welds develop stress fractures, composite materials delaminate as the bond between reinforcing fibers and matrix materials weakens under sustained environmental assault. The critical question is whether a spacecraft can carry sufficient spare parts and repair capability to counteract these degradation processes over voyage durations measured in centuries or millennia. The answer is almost certainly no for any journey beyond 400 years. Carrying replacement components for every system that might fail over a 1,000-year voyage would require a spare parts inventory approaching the mass of the original spacecraft, effectively doubling the mission mass and therefore doubling the propulsion energy required. Carrying manufacturing equipment capable of fabricating replacement parts from raw materials adds further mass and introduces its own reliability challenges, since the manufacturing equipment is itself subject to the same degradation processes afflicting everything else on board. The ship must carry machines to repair the machines that repair the ship, and those machines must themselves be maintained by yet another layer of backup systems, creating a regression of maintenance infrastructure that quickly becomes absurdly mass-intensive. The engineering reality is that every spacecraft has a maximum functional lifespan determined by the slowest degrading critical component that cannot be replaced or repaired en route. For current human technology, this lifespan is measured in decades. Even the most optimistic projections for advanced materials and self-repairing systems might extend functional lifespans to a few centuries. Beyond that, the cumulative statistical probability of cascading system failures, where one degraded component's failure overloads adjacent systems, triggering a chain reaction of breakdowns, approaches certainty. A ship that launches toward a star 10,000 light years away at 1% of light speed faces a million-year journey. No engineering architecture yet conceived or theoretically plausible could maintain spacecraft functionality across such a duration. The ship would arrive as a dead body, a monument to ambition, drifting silently past its intended destination with no functioning systems, no living crew, and no operational capability. Interstellar space does not merely impose time penalties on travel, it actively destroys the vehicle attempting to cross it, and timescales far shorter than the crossing itself requires for all but the nearest star destinations. But perhaps relativistic time dilation is an escape hatch. Special relativity predicts that time passes more slowly for objects moving at speeds approaching the speed of light relative to a stationary observer. This effect is real, experimentally confirmed to extraordinary precision using particle accelerators and orbiting atomic clocks, mathematically exact. For a spacecraft traveling at 90% of light speed, time on board the vessel passes at roughly 44% of the rate experienced by stationary observers who remained behind. At 99% of light speed, onboard time slows to approximately 14% of the external rate. At 99.9%, it compresses to about 45%. This means that a crew aboard a sufficiently fast ship could subjectively experience a galactic crossing in a fraction of the elapsed time measured by external observers. At 99.9% of light speed, the journey spanning 100,000 light years would feel like approximately 4,500 years to the crew on board, while 100,000 years pass for everyone and everything outside the ship. This sounds like a partial solution until you examine what it actually means for the civilization that built and launched the mission. Time dilation helps the travelers. It does absolutely nothing for the home world. While the crew experiences 4,500 years of subjective time, the civilization that designed, calculated, constructed and launched their vessels during 100,000 years of real, distinct, uncompressed historical. 100,000 years of evolution, cultural transformation, technological revolution, linguistic drift, religious change, ecological disruption, biological adaptation, and social reorganization. When the colony ship finally arrives at its destination on the far side of the galaxy, and its passengers step out into an alien star system, the civilization that sent them has not merely changed. It has been replaced dozens or hundreds of times over by successive societies as different from the original as modern humans. The language the colonists speak is incomprehensible to anyone alive at the origin. The cultural values they carry are archaeological curiosities. The technology they brought, which represented the cutting edge of their era, is now 100,000 years obsolete. The colony and the homeworld find themselves distant from each other. They are separated by a temporal abyss so profound that they share no meaningful cultural, linguistic, technological, or biological connection. They are strangers to any dimension that matters for coordinated civilization. This temporal severing is not a minor logistical inconvenience that could mitigate. It is a fundamental structural barrier to any form of coordinated galactic civilization. Even if you could send colony ships to distant regions of the galaxy at near light speeds, the colony would arrive in a future that bears no relationship to the past that launched it. There can be no coordination between network nodes separated by tens of thousands of years of independent divergent evolution. No shared governance across a network where direct central authority arrive at the destination after the authority itself is transformed beyond recognition. Memory multiple times over. Solve the expansion problem. Decrease the fragmentation problem by physically guaranteeing that a sufficiently distant colony becomes a fully independent civilization, culturally, technologically, and biologically, from the moment its ship enters cruise velocity. The connection to the origin is severed not by choice, but by physics. Now confront the energy constant. Even if a civilization accepted the penalties and the inevitable civilization fragmentation that relativistic travel imposes, physically generate enough energy to accelerate spaceflight as interstellar travel demands. The calculations are devastating. The kinetic energy of a moving object scales with the square of its velocity at non-relativistic speeds. At relativistic speeds, the relationship becomes dramatically more punishing due to the Lorentz factor, which causes the effective initial mass of the object to increase asymptotically as it approaches velocity. This means each incremental increase in velocity costs disproportionately more energy than the previous increment. Accelerating from rest to 10% of light speed is enormously expensive. Accelerating from 10% to 20% costs substantially more. Accelerating from 90% to 95% costs vastly more energy than the acceleration phase from 0 to 50%. The energy curve is not linear. It is not even simply contracting at relativistic velocities. It climbs towards infinity as speed approaches the modest interstellar spacecraft. The mass of the vessel, excluding fuel, is 1,000 metric tons. The mass of the International Space Station, a structure that required decades of multinational cooperation and hundreds of billions of dollars in low Earth orbit, just 400 kilometers below the surface. Accelerating this spacecraft to 10% of the speed of light requires approximately 5 times 10 to the 20th joules. For reference, the total annual energy consumption of all human civilization on Earth, every power plant, every vehicle, every industrial process, every light bulb, amounts to roughly 5.8 times 10 to the 20th joules per year. So accelerating a single ISS mass spacecraft to just 10% of light speed requires approximately 78% of humanity's annual energy production. Nearly the full energy output of every power plant, every vehicle, every industrial process on the planet for an entire year consumed by a single ship on a single one-way trip. And that calculation covers only the acceleration phase. The ship must also decelerate at the destination, which requires roughly the same energy expenditure again. And the fuel for deceleration must be carried on board from the start, added back to the vehicle, which increases the energy required for the initial acceleration, which demands more fuel, which adds to the cost. This vicious cycle is the tyranny of the rocket equation, and it is absolutely necessary to interstellar velocities. The rocket equation dictates that for any spacecraft carrying its own propellant, the ratio of total initial mass, including fuel to final dry mass, increases exponentially with the desired velocity change. For conventional chemical rockets, reaching even a small fraction of 1% of light speed requires fuel masses that would exceed the mass of the Earth. Chemical propulsion is categorically irrelevant for interstellar travel through velocity. More advanced propulsion concepts perform better, but still confront crushing constraints when you examine the actual numbers. Fusion propulsion, frequently cited as the most promising near-term interstellar technology, could theoretically achieve exhaust velocities of 3 to 5% of light speed, depending on the specific fusion reaction cycle employed and the efficiency of the magnetic confinement and nozzle systems. The deuterium-helium-3 fusion drive, pushing a 1,000 metric ton payload to 10% of light speed and then decelerating at the destination, would require a fuel mass of approximately 30 to 50,000 metric tons, depending on engine efficiency assumptions. This represents a fuel-to-payload ratio of 30 to 50. Assembling this quantity of fusion fuel would require mining and processing thousands of metric tons of isotopes from gas giant atmospheres, lunar regolith, or asteroid resources, then transporting, storing, and integrating this fuel with the spacecraft structure in deep space. The industrial infrastructure required to support a single such mission dwarfs any construction project in human history by orders of magnitude. And this entire colossal effort delivers exactly one ship to exactly one star. Antimatter propulsion offers the highest theoretical energy density of interstellar reaction. The annihilation of matter with antimatter converts approximately 100% of the rest mass into usable energy, compared to roughly 1% for nuclear fission and less than 1/2 of 1% for reactor chemical reactions. But antimatter carries a devastating practical limitation that collapses its price. Antimatter does not exist naturally in usable quantities anywhere across the universe. Every single microgram must be artificially manufactured using particle accelerators, and the production process is staggeringly, almost comically inefficient. Current technology at facilities like CERN produces antimatter with an energy efficiency of roughly 1 part in 10 billion. This means that generating 1 gram of antimatter requires approximately 10 billion times more energy input than the energy that gram would release upon annihilation. Even hypothetical far future antimatter factories operating at efficiencies millions of times better than energy would still consume more energy in production than the resulting antimatter could ever deliver. Antimatter propulsion does not solve the energy crisis of interstellar travel. It relocates the crisis upstream to the fuel manufacturing stage and ultimately amplifies it. Light sails represent a completely different architectural approach. Instead of carrying fuel on board, a light sail spacecraft is radiation pressure from a powerful laser array for departure. The spacecraft carries a propellant. All propulsive energy comes from the This elegantly eliminates the rocket equation as the fuel mass stays behind at the origin. The new Starship initiative was proposed using land-scale probes to Alpha Centauri at 20% of light speed, arriving at of flight time. The laser array required of this would need to produce approximately 1 coherent, precisely focused sustained for roughly 10 minutes per launch. much. 100 kilowatts is comparable to the total installed electrical generation of a mid-sized industrialized nation, firing simultaneously through a single direction. Now scale this concept from a gram-scale weight vessel massing thousands of metric tons. The required beam power scales linearly with pushing a 1,000 metric ton vessel to 20% of light speed using a laser sail would demand an output on the order of 100 million tons sustained throughout an extended acceleration phase, lasting weeks. This figure exceeds the sun's total volume discussed earlier by a substantial margin. A single column ship using light sail technology would require a laser installation more luminous than this, and the beam must remain precisely focused on distances that quickly grow to billions and billions of kilometers during the acceleration phase, requiring accuracy and optical coherence that make current state-of-the-art like Stone Age tools. Every propulsion physics reflects the same. Interstellar travel at velocities relevant to requires energy budgets that range from civilizations missions to physically impossible when scaled across thousands of destinations. And these calculations are individual voyages. A civilization's galactic expansion needs not one ship, but thousands, and tens of thousands. Each mission targets a different star system. Each carries enough mass to establish a colony or functional outpost. Each requires a full propulsion energy budget, its own fuel, its own manufacturing and assembly infrastructure. If a single mission to a single nearby star is energy equivalent to a significant fraction of that star's output, then 1,000 simultaneous missions to 1,000 different stars demand 1,000. 10,000 missions across a spiral require 10,000 times that. A galactic expansion campaign targeting even 1% of star systems would require cumulative energy expansion to the total luminous output of the entire galaxy, sustained continuously over millions of years. A common rebuttal proposes that advanced civilizations require energy from multiple stars, perhaps constructing structures like Dyson swarms that capture a large fraction of the star's total luminosity. This is theoretically conceivable, but creates a devastating strategy. Building a Dyson swarm around each requires disassembling and reprocessing entire raw material, an engineering project that will take centuries to millennia under even wildly optimistic assumptions about self-replicating robotic. A civilization that needs Dyson swarms around multiple stars to fund its expansion must first launch those stars to build the swarms, which requires exactly the energy the swarms are intended to generate. We need galactic energy infrastructure to expand across the galaxy. We need to have already expanded across the galaxy to build energy infrastructure. The logic is circular, and the circle does not close. Even ignoring the bootstrapping paradox, energy collected at one star can be efficiently transmitted to where it is needed across interstellar distances. Laser or microwave beams suffer from unavoidable diffraction-limited divergence. Over-separation is measured in light years. Even tightly collimated beams spread is measured in astronomical units, reducing received energy density to negligible fractions of what was transmitted. Physically transporting energy via fuel carriers and batteries requires ships, which consume a substantial portion of the energy they carry just to accelerate and decelerate. Energy does not flow across interstellar vacuum the way electricity flows through a continental power grid. It dissipates, and loses thermodynamic utility for a light year of distance. Each star system uses, for practical energy purposes, a self-contained that can utilize what it generates locally but cannot move through its energy to distant areas. One final dimension of the propulsion problem demands attention. The gap between building a single interstellar prototype and manufacturing an interstellar fleet at the scale galactic expansion required, solving the physics of one interstellar vessel requires a large material science capable of withstanding decades or centuries of deep space exposure, radiation and micrometeorite flux. Radiation adequate for biological or sensitive electronic data, autonomous navigation systems accurate across light scales, and power management systems that maintain functionality over mission durations exceeding any project ever attempted. But one ship is a prototype. Galactic expansion demands mass production at an unprecedented scale. Thousands of interstellar-rated vessels, tens of thousands, each loaded with colonization infrastructure, each launched on a unique trajectory toward a different destination. The industrial base required to manufacture this fleet is not a single factory complex. It is an entire civilizational economy reorganized around a single purpose, sustained across centuries of continuous production. The raw materials required: structural alloys, radiation shielding composites, fusion fuel cells, electronic components, biological supplies for crewed missions, would demand mining operations across multiple planetary bodies maintained for generations. Quality control standards for spacecraft that must operate autonomously for decades or centuries without any possibility of maintenance, repair, or resupply. Any manufacturing process is orders of magnitude, and every factory permanently depletes the home system's power. Metals fashioned into hull plating, fusion fuel burning, electronic components, biological, structural materials, all of it represents a one-way export of processed resources from the interstellar void. A civilization of 1,000 interstellar colony missions exported a significant fraction of material wealth. At some threshold, it exhausts its reachable reserves. The expansion program literally consumes the population it depends on. This generates a self-reliant that no technology can circumvent. Expansion phases target the nearest stars, energy and shortest transit times, or a fully stocked resource base. Each targets more distant stars. The mission requires longer transit times, a resource pool that has been partially depleted by every preceding wave. The marginal cost of expansion rises with every additional star system clear. Initial colonies are not easily achievable. A second shell of colonies further out becomes substantially harder. A shell harder still. Long before the expansion reaches even a small fraction of the galaxy's full extent, compounding costs of distance and the diminishing return grind the program to a halt. Expansion does not radiate outward in a smooth and solid way. It decelerates, it falters, it stalls. And it stalls not because of insufficient operation or inadequate engineering, but because the physics of collision mass and distance impose hard limits that can override. The speed of light sets a constant on velocity. Relativistic time guarantees that fast travel severs the temporal homeworld, ensuring civilizational physical inevitability rather than energy requirements for interstellar propulsion velocities scale to levels that stretch budgets for individual missions, and achievable when multiplied across the thousands of simultaneous missions, galactic expansion, fuel production and fleet manufacturing, non-renewable material resources, interstellar distances. And every propulsion concept within known physics, fusion drives, engines, light sails, or combining them, confronts the same fundamental limits when scaled from a single to a sustained galactic colonization. But suppose a civilization absorbed it. Suppose it accepted slow expansion. Suppose it tolerated civilization at the unavoidable cost of spreading out. Suppose it colossal energy and accepted the depletion of resources as the price of reaching new stars. Simply sent colonies outward in a gradual way, each colony becoming an independent entity with no expectation of maintaining cultural coherence across the growing network. Minimalist, bare bones values, not empire, not coordinated, just independent colonies spreading out. Encounters a barrier more fundamental than this. The colonies must still communicate, use navigational data to avoid redundant star systems. They must share critical information to prevent wasteful parallel development, warn each other of stellar hazards, resource shortages, and environmental dangers encountered at destinations. They must coordinate, at least minimally, to prevent as expansion fronts from different origins converge on the same regions. Even the loosest network of fully independent colonies provides a baseline flow of information between nodes. Like everything else in this universe, travels across galactic distances, arrive years, decades, centuries, or tens of millennia after the separation between sender and receiver. What examines what happens when a civilization any activity across a network where every signal is intelligence that is ancient. The barrier that kills galactic civilization. It is the absolute horrible silence that the universe imposes on it dares to spread beyond its own small neighborhood. Information obeys the same speed limit as light. Fact, which sounds like a minor footnote discussed previously, is actually the constraint facing any model of galactic civilization. Ships can theoretically be slow, stars over millennia and still eventually arrive. Information, commands, warnings, navigational updates, diplomatic negotiations, emergency calls, cultural transmissions, scientific discoveries must travel at the speed of light. There is no known mechanism, framework consistent with observed physics. Information to propagate faster than 792 kilometers per second in the vacuum of space. Every radio signal, every pulse, every modulated gravitational wave, every conceivable method of encoding and transmitting across interstellar distances is bound to an absolute ceiling. And at galactic scale, the ceiling transforms every act of coordination into communicating with ghosts. A signal sent from Earth to Alpha Centauri, the nearest star system at 4.24 light years, takes 4 years and roughly 3 months. The reply takes a duration to return. The minimum round trip between these closest stellar neighbors is approximately 2 years. This means that a question asked today is an answer until the mid-2030s. Decisions requiring back and forth negotiation, conflict resolution, trade terms, unfold across timescales, even between the two closest possible nodes in any interstellar network. For comparison, the average duration of a human government administration is 4 to 8 years. The single round-trip exchange with Alpha Centauri spans 1 to 2 political cycles. By the time an answer arrives, the government that asked the question may no longer exist. Now, extend the distance. A signal sent to a star system 50 light-years away takes 50 years to arrive. The round-trip delay stretches to a full century. The person who sent the message will likely be dead before the response returns. The institution that composed the message may have been restructured, defunded, or replaced. The political context that motivated the question may be entirely irrelevant. At 100 light years, a tiny fraction of the galactic diameter, the round trip spans 2 centuries. At 500 light years, the round trip takes a millennium. The civilization that receives the reply inhabits a world that has experienced 1,000 years of unshared history since the original message was dispatched. Languages evolve beyond mutual intelligibility within 500 to 1,000 years under conditions of separation. The English of the 11th century is functionally a foreign language to modern English speakers. A civilization receiving a reply after 1,000 years of isolation would need archaeolinguists to decode the returning message. At 1,000 light years, a round-trip communication takes 2 millennia. At 10,000 light years, the round trip stretches to 20,000 years. 20,000 years ago, the last ice age was still gripping the northern hemisphere. Humans had not yet invented agriculture. The entire arc of settled civilization, Sumer, Egypt, Greece, Rome, the Renaissance, the Industrial Revolution, the Space Age, fits within a single round-trip signal exchange across 10,000 light years. At 26,000 light years, the approximate distance from our solar system to the galactic center, a message sent today would arrive around the year 28,000. Any reply would return around the year 54,000. A civilization exchanging those messages would share nothing in common across that 52,000-year gulf, except perhaps basic biology. And even that might diverge given sufficient time and divergent evolutionary pressures. At the full galactic diameter of 100,000 light years, a single one-way message takes 100,000 years. A round-trip exchange requires 200,000 years. Anatomically modern humans have existed for approximately 300,000 years. A single round-trip communication across the galaxy consumes 2/3 of the entire existence of our species. Any entity attempting to govern, coordinate, or even loosely monitor a galaxy-spanning network faces feedback loops, measured not in days or months, but in geological epochs. The information arriving from the far side of the galaxy describes conditions that existed before the rise of every human civilization that has ever lived. It is not stale intelligence, it is paleontological data. These delays do not merely slow down coordination, they make coordination mathematically impossible beyond a certain network radius. To understand why, consider what coordination actually requires. At its most basic level, coordination means that 2 or more nodes in a network make decisions informed by knowledge of each other's current state. A supply chain works because the factory knows how much inventory the warehouse currently holds. A military command structure works because headquarters knows where its units are currently positioned. An economy works because buyers and sellers have approximately current information about prices, availability, and demand. Remove the word current from any of these systems, and they collapse into chaos. In an interstellar network, no node ever possesses current information about any other node. Every piece of data arriving from another star system describes conditions as they existed years, decades, centuries, or millennia ago, depending on distance. A colony 100 light years away that reports a critical shortage of rare earth elements is describing a crisis that began a century ago. By the time the message reaches the coordinating authority, the colony has either solved the problem independently, adapted its technology to work without those elements, collapsed entirely, or evolved its society in directions the coordinating authority cannot predict. Any response dispatched from the authority will take another century to arrive, delivering a solution to a problem that has been resolved, transformed, or forgotten for 200 years. The response is not helpful. It is an archaeological curiosity arriving from a distant past that no longer has any bearing on the colony's present reality. This is not a failure of bandwidth or signal strength. Increasing the data rate does not help. Sending 1,000,000 bits per second instead of 1,000 bits per second still delivers information that is 100 years out of date. The problem is latency. not throughput, and latency is fixed by the speed of light and the distance between nodes. No technology can reduce it. No relay system can accelerate it. No compression algorithm can compensate for the fact that the information describes a reality that no longer exists by the time it arrives. Now consider what happens as the network grows. A civilization spanning 10 star systems within a radius of roughly 20 light-years faces communication delays of up to 40 years for round-trip exchanges between the most distant nodes. This is difficult but arguably manageable for a long-lived civilization with stable institutions. Decisions can be made on generational timescales. Cultural coherence can be maintained through regular exchanges of media, scientific publications, and diplomatic correspondence, even if each exchange takes decades. The network is small enough that the lag, while painful, does not fundamentally break the ability to function as a loosely connected entity. Expand the network to 100 star systems, spanning perhaps 200 light-years. Round-trip delays between the most distant nodes now reach 400 years. No government structure in recorded human history has survived 400 years without radical transformation. The Roman Republic lasted roughly 5 centuries before becoming the Roman Empire, which itself fragmented and fell within another 5 centuries. The civilization at one edge of this 100-system network cannot meaningfully govern, trade with, or culturally synchronize with the civilization at the other edge, because 4 centuries of independent development separate every exchange. Different nodes begin developing divergent technologies, divergent social structures, divergent languages, and divergent priorities. The network does not merely stretch, it begins to fracture along lines defined by communication delay. Expand further to 1,000 star systems across 2,000 light-years. Round-trip delays between extremes hit 4,000 years. This exceeds the entire lifespan of every empire in human history combined. The nodes at opposite ends of this network are not members of the same civilization in any meaningful sense. They cannot coordinate economic activity because price signals arrive millennia too late to be actioned. They cannot coordinate defense because threat warnings arrive after the threat has either been resolved or has conquered the warned system a year ago. They cannot share scientific knowledge effectively because discoveries transmitted from one end arrive at the other after the receiving civilization has independently developed equivalent or superior knowledge through its own 4,000-year research program. The network is not a civilization. It is a constellation of independent civilizations that happen to share distant ancestry, communicating through messages that carry the informational value of ancient scrolls discovered in archaeological digs. This escalating breakdown is a mathematical pattern that can be described as coordination decay. As the number of nodes in the network increases, the number of unique pairwise communication channels grows proportionally to the square of the node count. 10 nodes require 45 unique channels. 100 nodes require 4,950 channels. 1,000 nodes require nearly 500,000 channels. 10,000 nodes require approximately 50 million channels. Each channel carries its own latency penalty, determined by the distance between the 2 nodes it connects. Managing this network means processing information from millions of channels, each delivering data with a different time, each describing conditions at a different historical time, each requiring interpretation in the context of a reality that has evolved independently since the data was transmitted. The computational challenge of maintaining coherence across such a network is not simply large, it is fundamentally intractable. The information required to make an optimal coordinating decision for the network as a whole includes the current state of every node. But the current state of every node is unknowable because it can only be inferred from data that is years or centuries out of date. Any decision based on this stale data is a decision made in partial ignorance. As the network expands and delays increase, the fraction of relevant information that is actually current shrinks towards zero. Eventually, the coordinating authority is making decisions based almost entirely on historical data that bears no relationship to present conditions at any time. At that point, central coordination is not merely inefficient, it is actively harmed, because decisions optimized for conditions that existed centuries ago would be wrong for conditions that exist now. Nodes are better off making independent decisions based on local information than following directives issued by a distant authority operating on ancient data. This is not speculation about alien psychology or political philosophy. It is an information theoretic constraint that applies to any network of any kind: biological, electronic, social, or political, where the latency of communication between nodes exceeds the timescale on which conditions in those nodes change. When the lag exceeds the rate of change, coordination becomes impossible regardless of the intelligence, goodwill, or computational power of the coordinating entity. The galaxy imposes communication lags measured in millennia. Civilizations change on timescales measured in centuries or less. The mismatch is fatal to every model of coordinated galactic governance. Resource coordination faces a more specific version of this collapse. Civilization is not merely exchanging abstract messages. It must allocate physical resources, energy, raw materials, manufactured goods, biological stocks, technological components across its network of star systems. Some systems will be resource rich, others will be resource poor. Some will specialize in energy production, others in manufacturing, others in agriculture or biological sciences. Any functional multi-system economy requires that resources flow from where they are abundant to where they are needed. Guided by information about supply and demand at each node, the resource shipments between star systems travel at speeds far below light speed. Even the most optimistic propulsion scenarios will already claim place interstellar transit times for physical cargo at decades to centuries for nearby stars and millennia to millions of years for distant ones. A shipment of critical materials dispatched from a mining colony to a manufacturing hub 50 light years away will take centuries to arrive, even at an ambitious fraction of light speed. The manufacturing hub must plan its production schedule around supply shipments that were dispatched generations ago, based on demand forecasts made centuries before the shipment arrives. If demand has shifted during the transit period, which it certainly will have, given that entire technological paradigms can rise and fall within a few centuries, the arriving shipment may contain materials that are no longer needed in quantities that no longer match requirements, produced to specifications that are no longer compatible with current manufacturing systems. Supply chain management is one of the most complex coordination problems in modern economics. Even when communication delays are measured in milliseconds and shipping times in days, introduce communication delays of years and shipping times of centuries, and the entire framework of supply chain logistics ceases to function. There is no algorithm, no predictive model, and no artificial intelligence system that can accurately forecast demand across centuries of civilizational development at a distant node. The variables are too numerous, the interactions too complex, butterfly effects too pervasive. A star system that urgently needs titanium alloys today might need synthetic organic compounds by the time the titanium shipment arrives 3 centuries from now. The sending system has no way to know this because the demand signal will not reach them for another 50 years, by which time the receiving system's needs will have changed again. This logistical paralysis extends to every form of physical exchange. Technology transfer becomes meaningless when the transmitted blueprints describe manufacturing processes state-of-the-art at the same node centuries ago, hopelessly obsolete by the time they arrive. Military reinforcements dispatched to assist a threatened colony centuries after the threat has been resolved one way or another. Medical knowledge shared between star systems arrives after the diseases it addresses have either been independently cured or evolved beyond the treatment's efficacy. Cultural knowledge, literature, music, art, philosophical traditions arrive as historical artifacts from a foreign civilization, rather than as contemporary contributions to a shared culture. The net effect is that each star system in the network becomes functionally self-sufficient, not by choice but by necessity. Relying on imports that take centuries to arrive is not a viable economic strategy. Waiting for instructions from a distant capital that will not arrive for military is not a viable government strategy. Depending on military allies whose reinforcements will show up long after the war has ended is not a viable security strategy. Each node must develop its own complete resource extraction, manufacturing, energy production, scientific research, medical, agricultural, and defensive capabilities independently, because the network cannot deliver any of these things on timescale relevant to the node's actual needs. But a star system that must be entirely self-sufficient in every domain has no functional need for the network. The network provides nothing that local self-sufficiency does not already supply. Connections between nodes become ceremonial, symbolic links to a shared ancestral heritage, rather than functional channels delivering actual value. The civilization has been spread across the galaxy. It has shattered into thousands of independent civilizations that share a common origin and nothing else of practical significance. The impossibility of interstellar resource coordination has a specific economic consequence that deserves explicit examination, because it demolishes the foundational premise of every fictional galactic economy ever imagined. Interstellar trade, the exchange of physical goods between star systems for mutual economic benefit, is not merely impractical at galactic scales. It is thermodynamically nonsensical. Trade functions when the cost of transporting a good from producer to consumer is less than the value that good provides to the consumer. On Earth, shipping a container of electronics from Shenzhen to Los Angeles costs a few $1,000s and takes roughly 2 weeks. The electronics inside are worth far more than the shipping cost, so the trade is profitable and therefore sustainable. Now apply this logic to interstellar distances. Shipping physical cargo between star systems requires accelerating that cargo to a certain fraction of light speed, sustaining the voyage across decades of transit, and decelerating at destination. As we have already seen, the energy cost of accelerating even modest masses to interstellar velocities is comparable to the annual energy output of entire civilizations. The energy cost of shipping 1 metric ton of material to a star system 10 light years away dwarfs the value of that material by factors of millions or billions, regardless of how rare or precious the material may be. There is no substance in the periodic table, no element, no alloy, no manufactured component whose value per kilogram could justify the energy expenditure required to ship it across interstellar distances. Gold, platinum, enriched uranium, advanced microprocessors. The energy cost of delivery exceeds the utility value of the delivered goods by so many orders of magnitude that the transaction is thermodynamically absurd. You would earn more wealth in fuel than you could ever recover from the cargo delivered. Even information trade, the exchange of scientific data, cultural products, and technological blueprints encoded as electromagnetic signals, faces crippling limitations beyond the latency problems already discussed. Information has economic value only when it arrives in time to be acted upon, and only when the receiving civilization possesses the context and infrastructure to use it. A blueprint for a revolutionary new energy system, transmitted from star system A to star system B, arrives decades or centuries later. During that transit time, star system B has independently developed its own energy technology, optimized for its own local conditions and resources. The arrival blueprint describes a system designed for star system A's specific environment, its available materials, its stellar energy spectrum, its gravitational conditions, its atmospheric chemistry. Adapting the design to star system B's entirely different conditions requires engineering effort equivalent to designing a new system from scratch. The transmitted information provides negligible advantage over independent local development because the contexts have diverged too far for direct technology transfer to function efficiently. Financial systems face an even more fundamental challenge. Money functions as a medium of exchange, when both parties in a transaction share a common monetary framework, a currency, a banking system, a mechanism for enforcing contracts and settling debts. across interstellar distances with communication rates measured in decades or centuries, no shared financial framework can operate. You cannot extend credit across a 3-year communication lag because the borrower's economic conditions will be transformed beyond recognition before the lender receives even the first status update. You cannot deposit in a common currency because currency values fluctuate based on economic conditions that diverge independently to each species. You cannot enforce contracts because the legal systems of each node evolve independently, and any enforcement mechanism requires communication and physical presence that the distances involved make impossible. The entire apparatus of finance, banking, insurance, futures markets, and other instruments depends on timely information flow and enforceable agreements between parties. Remove timely information flow and enforceability simultaneously, and financial systems do not merely become efficient, they become logically incoherent. There is nothing to trade, no way to pay, no mechanism to enforce delivery, and no framework to adjudicate disputes across communication gaps measured in human lifetimes. There is a tempting counter-argument that deserves direct confrontation. Perhaps a galactic civilization would not attempt centralized coordination at all. Perhaps it would adopt a decentralized model, allowing each colony full autonomy while maintaining the network purely for information sharing rather than control. Each node governs itself, makes its own resource decisions, develops its own technology, and simply broadcasts its accumulated knowledge outward for any other node that might find it useful. No central authority, no coordinated resource allocation, no governance hierarchy, just a loose web of independent civilizations, sharing information at the speed of light. This model is more robust than centralized coordination, but it still fails at galactic scales. Even passive information sharing requires that the information be useful when it arrives. Scientific data transmitted from one node to another remains valuable only if the receiving node's technological context has not diverged so far that the data is incomprehensible or irrelevant. The breakthrough in quantum computing transmitted to a node that independently abandoned electronic computation 2 centuries ago in favor of biological neural networks provides no value. The two civilizations have diverged down incompatible technological paths. Their knowledge bases no longer overlap sufficiently for transmitted data to be integrated into the receiving civilization's framework. This technological divergence is not hypothetical. It is inevitable given sufficient time and independence. Civilizations facing different environmental challenges, different resource availabilities, different biological makeups, and different cultural priorities will develop different technologies. A colony orbiting a red dwarf star in a resource-poor system will develop entirely different engineering solutions than a colony in a resource-rich system orbiting a sun-like star. Over centuries of independent development, their technological traditions will become as mutually incomprehensible as the engineering principles of medieval European cathedral builders and modern semiconductor fabricators. Both are sophisticated, both solve real problems, but neither can meaningfully contribute to the other's work without extensive translation and context building, that itself takes generations. Language drift compounds the problem catastrophically. Human languages mutate, branch, and diverge on timescales of centuries. After roughly 1,000 years of separation, two populations descended from the same linguistic stock will speak mutually unintelligible languages. After 5,000 years, the languages may share so few common roots that the relationship is undetectable without sophisticated comparative analysis. A galactic network where signals take thousands of years to traverse experiences exactly this kind of linguistic fragmentation. Messages arriving from distant nodes are not merely delayed, they are encoded in languages that the receiving civilization no longer speaks, references cultural concepts that the receiving civilization does not share, and uses technical terminology that maps to no equivalent in the receiving civilization's vocabulary. Decoding these messages becomes a task for historians and linguists rather than administrators and engineers. The information channel has not been severed. Photons still arrive carrying modulated signals, but the semantic content of those signals has become inaccessible without scholarly interpretation and itself introduces delays and potential misunderstanding. Even mathematical and scientific notation, often proposed as universal languages immune to cultural drift, cannot fully escape this problem. Mathematical truths are universal, but mathematical notation is not. The way a civilization encodes, transmits, and interprets mathematical relationships depends on its notational conventions, its computational paradigms, its conceptual frameworks, and its educational traditions. Two civilizations that have independently developed advanced mathematics may arrive at equivalent truths expressed in mutually incompatible formalisms. Translating between these formalisms is possible in principle, but requires sustained scholarly effort that consumes time and intellectual resources that can be spent on independent research. The cost of maintaining inter-civilizational communication compatibility eventually exceeds the benefit of the information received, at which point rational nodes simply stop trying to decode incoming signals from distant, divergent sources. The communication barrier also destroys the ability to maintain consistent standards across the network. Technological compatibility requires shared standards, common units of measurement, compatible data formats, interoperable hardware specifications, agreed upon communication protocols. On Earth, maintaining international standards requires constant committee work, regular updates, and ongoing negotiation between parties that can communicate in real time. Now imagine maintaining technological standards across a network where the standards body publishes an update that takes 500 years to reach the most distant node. By the time the update arrives, the distant node has independently developed 3 generations of incompatible replacement standards optimized for its own local conditions. It has no incentive to adopt the centrally published standard, because doing so would require scrapping centuries of locally optimized infrastructure in favor of a specification designed half a millennium ago for conditions that may never have existed at the distant node's location. Without shared standards, physical interoperability between nodes becomes impossible. A spacecraft designed and built at one star system cannot dock at facilities designed at another system thousands of light years away, because their engineering specifications diverged centuries ago. Fuel produced at one node is incompatible with engines designed at another. Data formats are mutually unreadable. Communication protocols are mutually unintelligible. The network's physical infrastructure fragments into thousands of locally optimized but mutually incompatible subsystems. There is no galactic internet because there is no agreed upon protocol stack. There is no galactic trade because there are no compatible cargo standards. There is no galactic military because there are no interoperable weapon systems or command structures. Each node is a sealed pocket of locally coherent technology surrounded by mutual incompatibility imposed not by hostility or negligence, but by the simple impossibility of maintaining shared standards across communication delays measured in centuries and millennia. The cumulative effect of all these communication-driven breakdowns can be summarized in a single principle. Coherent coordination requires that the communication latency between nodes be shorter than the timescale in which conditions at those nodes change significantly. When latency exceeds the rate of change, coordination degrades. When latency vastly exceeds the rate of change, as it does at galactic scales, coordination collapses entirely. What remains is not a civilization, but an archipelago of independent societies, connected by threads of ancestral memory, growing thinner and more tenuous with every passing century. This principle imposes a maximum coherent radius on any interstellar civilization. The exact radius depends on assumptions about how quickly civilizations change and how much latency coordinated systems can tolerate. If a civilization can tolerate round-trip delays of up to 50 years, roughly one human lifetime, then the maximum coherent radius is approximately 25 light years. This encompasses perhaps a few dozen star systems. If a civilization with exceptionally stable institutions could tolerate round-trip delays of up to 500 years, The maximum coherent radius extends to roughly 250 light-years. This might include a few thousand star systems. If an immortal, post-biological civilization with perfect institutional continuity could tolerate round-trip delays of 5,000 years, already an extraordinarily generous assumption, the coherent radius reaches approximately 2,500 light-years, encompassing perhaps tens of thousands of star systems. Even the most generous estimate, 2,500 light-years, represents only 2.5% of the galactic diameter. A civilization pushing coherence to its absolute theoretical maximum would still control less than 1,000th of the galaxy's volume, and this maximum assumes perfect institutional stability over millennia, instantaneous internal decision-making, zero technological drift between modes, and a tolerance for communication delays that no known civilizational structure has ever demonstrated. In practice, the coherent radius is almost certainly far smaller, measured in tens or hundreds of light-years. The galaxy is simply too large, and the speed of light too slow for any coordinating intelligence to maintain meaningful influence across more than a tiny fraction of the galactic disk. This does not mean interstellar civilizations are impossible. Small clusters of nearby star systems could plausibly maintain some degree of coordination, exchanging messages and resources across delays of years or decades. These local clusters would function as independent civilizational units, stellar neighborhoods bound together by manageable communication lags and feasible resource exchange timescales. But the clusters themselves would be isolated from one another by gaps that impose communication delays beyond any coordinating system's tolerance. The galaxy would not host one civilization. It would host thousands or millions of small, independent, mutually isolated civilizational clusters separated by communication barriers as impenetrable as any physical wall. But communication collapse, devastating as it is, still leaves one final line of defense for proponents of galactic expansion. Perhaps individual colonies need not coordinate at all. Perhaps each colony simply survives independently, reproducing the expansion process from its own local position, sending out daughter colonies that send out their own daughter colonies in an ever-expanding wave of autonomous settlement, requiring no communication, no coordination, no shared standards, and no central authority. Just biology, doing what biology does, reproducing and spreading outward. Even this minimalist model, stripped of every coordinating function, faces a final and inescapable physical barrier. Every colony, every outpost, every autonomous settlement must fight a war it can never win permanently. The war against entropy. Every structure degrades, every energy source depletes. Every isolated system trends toward disorder over time. Maintaining a colony against the relentless pull of thermodynamic decay requires constant energy input, constant material renewal, constant active resistance against the universe's most fundamental tendency. Scaling this fight across thousands of independent colonies, separated by light years of empty vacuum, sustained over millions of years of galactic time, introduces constraints that make even the communication barrier look forgiving. But there remains one final enemy deeper than all the others, not distance, not speed, not silence, but the thermodynamic reality that the universe is an entropy machine, and every structure built within it is temporary. The second law of thermodynamics is the most democratically enforced in all of physics. It does not care how intelligent you are. It does not care how advanced your technology has become. It does not care whether you are a single-cell organism akin to a hydrothermal vent or a post-biological superintelligence commanding the energy output of an entire star. The second law states that the total entropy of any isolated system, its measure of disorder, randomness, and thermodynamic must increase over time. Energy degrades from concentrated useful forms into dispersed, unusable waste. Ordered structures decay into disordered rubble. These arrangements of matter trend relentlessly towards simple, more probable configurations. This is not a tendency that can be reversed by clever engineering. It is the statistical consequence of how energy and matter behave at the most fundamental level of physical reality. You can fight entropy locally by pumping energy into a system to maintain its order, just as a refrigerator fights the natural tendency of heat to equalize by continuously consuming electricity. But every local victory against entropy comes at a global cost. The energy used to maintain local order generates waste heat that increases entropy elsewhere by an even greater amount. The universe's total entropy always rises, always, without exception. And this law, more than distance, more than the speed of light, more than the energy crisis of propulsion, is the deepest reason why galaxy-spanning civilization is physically unstable. Every structure ever built by any civilization requires continuous energy input merely to continue existing. The building must be maintained against weather, erosion, settling, and material fatigue. The computer must be powered, cooled, and periodically repaired as components degrade. The biological organism must eat, breathe, and repair cellular damage every moment of its life. Stop the energy input and the structure decays. This is not a flaw in design. It is the fundamental thermodynamic cost of maintaining any ordered system in a universe that trends toward disorder. The more complex the structure requires to resist entropy. A mud hut requires minimal maintenance. A skyscraper requires enormous ongoing investment in structural repair, climate control, elevator maintenance, plumbing, and electrical systems. A space station requires constant monitoring and replacement of cylinders, filters, radiation shielding, atmospheric recyclers, and thermal efficient systems. An interstellar colony, a fully self-sustaining habitat operating in the vacuum of space, on the surface of an alien world with no supply lines to any external civilization, represents the most maintenance-intensive structure imaginable. Every component must be locally manufactured, repaired, or replaced from locally available resources. Every failure cascade must be locally contained and corrected. Every energy system must be locally fueled and locally maintained. The thermodynamic cost of keeping a single interstellar colony functional is staggering, even under optimistic assumptions about technology and resource availability. Now multiply this maintenance burden across thousands of colonies spread over thousands of light years. Each colony fights its own independent war against entropy, using only the energy and materials available in its local star system. Some systems will be energy-rich, orbiting bright, stable stars with abundant planetary resources for manufacturing replacement components. These colonies might sustain themselves for millions of years, continuously repairing, upgrading, and replacing degrading infrastructure. Other systems will be energy poor, orbiting dim red dwarfs or sitting in resource-scarce environments where critical raw materials are difficult to extract. These colonies will face a constant thermodynamic deficit, spending more energy on maintenance than their local environment can sustainably provide. Over centuries and millennia, they will fall behind the entropic curve. Systems will fail faster than they can be repaired. Infrastructure will degrade faster than it can be replaced. The colony will simplify, shrink, and eventually collapse, not because of any dramatic catastrophe, but because the slow, grinding arithmetic of entropy eventually overwhelms any finite energy budget. This entropic attrition is not a dramatic event. It does not announce itself with explosions or alarms. It is a gradual statistical process operating on timescales of centuries and millennia. A colony that is thriving in its first 1,000 years might begin showing signs of strain in its second 1,000. As original infrastructure reaches the end of its functional lifespan, and replacement components prove slightly less reliable, then the original is due to accumulated manufacturing drift. By the third millennium, critical systems might require workarounds and jury-rigged repairs because the precision manufacturing capabilities needed to produce exact replacements have themselves degraded. By the fifth millennium, the colony's technological capabilities may have regressed immeasurably from their initial level, not because the colonists became less intelligent, but because the cumulative burden of maintaining complex systems without external inputs inevitably erodes the technological base over sufficiently long timescales. This process is called technological regression, and it has abundant historical precedent even on Earth, where supply lines are short and civilizational neighbors are close. The Roman Empire at its height maintained engineering capabilities, concrete formulations, aqueduct construction, road building techniques, architectural methods that were lost for centuries after the empire's fall, not because the knowledge was deliberately destroyed, but because the institutional, economic, and logistical infrastructure required to sustain those technologies could not be maintained once the imperial system that supported them fragmented. Medieval Europe could not reproduce Roman concrete for roughly 1,000 years. The technology existed in written records. The knowledge was theoretically available, but the complex industrial supply chains, specialized training programs, and institutional continuity required to actually implement that technology had decayed beyond recovery. Now imagine this regression dynamic operating on an interstellar colony with no external civilization to eventually rediscover what was lost. Every technological capability that degrades is gone permanently unless the colony independently reinvents it from first principles using whatever diminished resources remain available. Stellar timescales add another layer of entropic constraint that operates above and beyond the maintenance burden of individual colonies. Stars are not eternal. They are nuclear furnaces consuming finite fuel supplies on timescales measured in billions of years. Sun-like stars, spectral class G, the type that hosts our own solar system, burn through their hydrogen fuel in approximately 10 billion years. Our sun is currently roughly halfway through its main sequence lifetime. In approximately 5 billion years, it will exhaust its core hydrogen, swell into a red giant that engulfs the inner planets, and eventually shed its outer layers to leave behind a smooth-feeling white dwarf. Any colony orbiting a sun-like star has a maximum operational window dictated by that star's remaining sequence lifetime. After that, the colony's primary energy source transforms in ways that render the local habitable zone uninhabitable. Red dwarf stars offer much longer lifetimes. The smallest red dwarfs will burn for trillions of years, far longer than the current age of the universe. A colony orbiting a stable red dwarf theoretically has access to a nearly inexhaustible energy source on any timescale relevant to civilizational survival. But red dwarfs present their own challenges. They are significantly dimmer than sun-like stars, meaning habitable zone planets must orbit extremely close to their host star. At such close distances, tidal locking becomes likely, creating permanent day and night hemispheres with extreme temperature differentials. Red dwarfs are also prone to intense stellar flares that constrict planetary atmospheres and irradiate surfaces with lethal doses of ultraviolet and X-ray radiation. A colony orbiting a red dwarf gains longevity that pays for it with a harsher, less stable local environment that imposes its own chronic maintenance burdens. More massive stars, spectral classes O, B, and A, burn far hotter and faster, exhausting their fuel in tens or hundreds of millions of years rather than billions. These stars offer enormous energy output, but on timescales too short for any slow expanding civilization to fully exploit. A colony established around a bright B-type star might enjoy tremendous energy abundance, but face the star's death within 100 million years, forcing either evacuation to a new system, with all the propulsion and energy processes already established, or extinction. The diversity of stellar lifetimes means that a galactic civilization colonies does not age uniformly. Different nodes in the network face different energy timescales, depending on their host stars. Some colonies lose their primary energy source after a few 100 million years. Others persist for billions. Coordinating a network where different nodes have fundamentally different operational lifespans adds yet another layer of complexity to an already impossible management problem. And over the truly long timescales that galactic expansion requires, tens of millions to billions of years, the stellar population of the galaxy itself changes. New stars form in molecular cloud nurseries. Old stars die in supernova explosions or quietly fade as white dwarfs. The galactic environment is not a static stage on which civilizations can build permanent structures. It is a churning, evolving system where the very energy sources that colonies depend upon are themselves temporary features of the landscape. The galaxy's rotation compounds this temporal instability. The Milky Way, as we have already seen, rotates differentially, with inner regions completing orbits faster than outer regions. A single galactic rotation takes approximately 230 million years. Over the timescales required for galactic expansion, certainly tens of millions of years and more likely hundreds of millions, the galaxy completes significant fractions of a full rotation. Stars that were adjacent to the starting expansion program would have drifted to entirely different galactic neighborhoods by the time the program reaches its final phases. Spiral arms, which are density wave patterns rather than fixed material structures, are propagated through the disk, sweeping some colony systems into denser environments and leaving others stranded in interarm voids. The physical map of the galaxy that any expanding civilization relied upon becomes obsolete on timescales shorter than the expansion itself requires. Building a permanent network across a structure that rearranges itself every few hundred million years is not really difficult. It is building on foundations that are guaranteed to shift beneath you. Now consider the thermodynamic cost of maintaining network infrastructure, specifically the relay stations, communication beacons, navigational markers, and resource depots that any interstellar network requires between its primary colony nodes. Every piece of infrastructure positioned in interstellar space, away from the host star, lacks access to continuous stellar energy. It must either carry its own power supply, nuclear reactors, radioisotope generators, or stored energy reserves that deplete over time, or receive beamed energy from a distant star system, suffering the same catastrophic transmission losses we have already encountered. Either way, the infrastructure has a finite operational lifetime, determined by its energy reserves or the reliability of its energy supply link. A communication relay station midway between two star systems, 50 light-years apart, sits 25 light-years from the nearest energy source. Beaming energy to the star system suffers the same catastrophic reflection, divergence losses that plague all interstellar energy transmission. The relay must therefore carry its own onboard power supply. A nuclear fission reactor using uranium fuel might operate for a few decades before requiring refueling. Refueling that requires a physical mission from the nearest colony, taking decades or centuries to arrive depending on propulsion technology. A radioisotope thermoelectric generator using plutonium-238 has a half-life of roughly 87 years, meaning its power output drops by half every 87 years. After a few centuries, the generator produces insufficient power to operate the relay's communication systems. The relay goes dark. The link between the two star systems it served is severed. Replacing or refueling dead relays requires dispatching maintenance missions, ships carrying fuel, replacement parts, or entirely new relay hardware across interstellar distances. Each maintenance mission incurs the same energy and time costs as any other interstellar voyage. A network of thousands of relays spread across thousands of light years would require a continuous pipeline of maintenance missions cycling between colony systems and relay positions, each mission consuming energy and resources that could otherwise be used for colony maintenance or new expansion. The maintenance burden of the network infrastructure alone becomes a significant thermodynamic drain on the civilization's total energy budget. At some network density and extent, the energy required to maintain the network's connected infrastructure exceeds the energy the network's colonies can spare from their own local survival needs. The network becomes a thermodynamic parasite, consuming more resources to maintain its connections than those connections provide in value. At that point, rational nodes will stop investing in network maintenance because the return on investment has gone negative. They will focus their finite energy budgets on local survival, rather than maintaining links to distant systems that provide no actionable benefit. The network does not collapse because of a single catastrophic failure. It withers because the economics of entropy make its maintenance unsustainable at sufficient scale. All of these constraints, colony-level entropic decay, stellar lifetime limitations, galactic rotation, and network infrastructure maintenance costs, converge on a single concept that defines the ultimate physical limit on interstellar civilization, the galactic fragmentation horizon. This is the maximum radius from any central point, any homeworld, any founding colony, any civilizational core, at which a connected, coordinated civilization can maintain physical viability before the combined effects of communication delay, energy transmission losses, entropic maintenance costs, and temporal instability make coherence impossible. The fragmentation horizon is not a single fixed number. It depends on the technological level of the civilization, the efficiency of its energy systems, the stability of its institutions, and its tolerance for communication delay. But even under extraordinarily generous assumptions, the horizon is small relative to the galaxy. A civilization with fusion-level energy technology, highly efficient life support systems, and institutional stability spanning millennia might maintain coherent coordination across a radius of a few hundred light years. This would encompass perhaps several thousand star systems, a substantial interstellar presence by any measure, but one that occupies a volume representing far less than 1% of the galactic disk. A hypothetical post-biological civilization with near-perfect energy efficiency, effectively immortal institutional memory, and tolerance for communication delays measured in thousands of years, might push the horizon to perhaps 1,000 or 2,000 light years. This would encompass tens of thousands of star systems, impressive, but still representing a tiny level of the vast darkness of the entire galaxy. Beyond the fragmentation horizon, colonies are not lost or destroyed. They simply become independent. They continue to exist, to evolve, to develop their own cultures and technologies and aspirations. But they are no longer part of the founding civilization in any functional sense. They are daughter civilizations, related by ancestry, divergent in practice, and increasingly alien to one another as centuries and millennia of independent development accumulate. The galaxy does not fill with one expanding civilization. It fills, if it fills at all, with thousands or millions of small civilizational clusters, each bounded by its own fragmentation horizon, each operating independently, each separated from its neighbors by gulfs of space and time that no communication or transport system can meaningfully bridge. This is not the dramatic, catastrophic failure that science fiction imagines when galactic empires fall. There are no rebellions, no interstellar wars, no dramatic collapses driven by corruption or tyranny. The fragmentation is quiet, structural, and inevitable. It is imposed not by the failings of the civilization, but by the geometry of space, the speed of light, the thermodynamics of energy, and the hour of time. A civilization that expands beyond its fragmentation horizon does not fail. It succeeds locally and fragments globally. It creates pockets of interstellar achievement surrounded by distances that guarantee those pockets will never cohere to a unified galactic whole. This understanding reframes the question that motivates so many discussions about galactic civilization. The famous Fermi paradox asks why, given the vast number of stars and the enormous age of the galaxy, we see no evidence of galaxy-spanning civilizations. The question assumes that a sufficiently old and advanced civilization would naturally expand toward the galaxy, making its presence obvious through megastructures, communication signals, or direct physical evidence. The physics examined across this episode suggests a different answer. The galaxy is not empty because civilizations fail, destroy themselves, or never arise. It may be quiet because the physical structure of the universe makes galaxy-spanning coherence impossible. Civilizations may arise frequently, or may achieve interstellar travel. They may establish colonies around nearby stars and build thriving multi-system cultures hundreds of light years. But they do not fill the galaxy, because filling the galaxy requires sustaining coordinated expansion across 100,000 light years of space and millions of years of time. against the combined resistance of light speed delay, energy scarcity, entropic decay, and temporal instability, the expansion fragments. The fragments persist as local clusters. The clusters never merge into a galactic whole, because the physics that fragmented them continues to operate on every scale. The Milky Way is represented with thousands of small civilizational clusters, each occupying a few hundred or a few thousand light years of space, each invisible to the others across the galaxy as a stellar eclipse that separate. From within any one cluster, the galaxy appears empty and silent, not because no other civilizations exist, but because those civilizations are too distant, too isolated, and too divergent for their signals to be detectable, interpretable, or meaningful. Silence is not evidence of absence, it is evidence of distance. The universe does not forbid intelligence. It forbids the coherent propagation of intelligence across scales that exceed the physical limits imposed by thermodynamics, relativity, and the structure of space-time. This conclusion does not declare galactic expansion absolutely impossible. It would be intellectually dishonest to claim that no civilization, under any conceivable circumstances, could ever establish any presence beyond its fragmentation horizon. Slow diffusion of independent colonies, each founding its own local cluster, each cluster eventually spawning its own joint colonies that found their own clusters, could theoretically seed the galaxy with life over timescales of hundreds of millions of years. But this process would not produce a galaxy-spanning civilization. It would produce a galaxy populated by millions of independent, mutually isolated civilizational islands, each one unaware of most of the others, each one evolving along its own unique trajectory, each one bounded by the same fragmentation horizon that limited its parent culture. The galaxy would be alive but not unified, populated but not connected, full of intelligence but devoid of empire. The universe favors isolation. This is not a punishment imposed on civilizations for some cosmic transgression. It is not a filter designed to test the worthiness of intelligent species. It is a structural property of physical reality as fundamental and as impartial as gravity itself. The speed of light creates communication horizons that shrink effective network size to tiny fractions of the galactic volume. The thermodynamics of entropy impose maintenance costs that drain finite energy budgets and cause technological regression overload. The finite lifetimes of stars guarantee that the energy sources humans depend upon are themselves temporary. The differential rotation of the galaxy rearranges the physical landscape faster than any expanding civilization can map and adapt to it. And the cubic scaling of three-dimensional volume ensures that every increment of expansion radius demands disproportionately more resources, more energy, more coordination capacity, and more maintenance than the increment before it. These are not problems that better technology can solve. They are constraints embedded in the fabric of the universe at the deepest level of physical law. A civilization a million years more advanced than humanity would face the same speed of light. It would face the same second law of thermodynamics. It would face the same finite stellar lifetimes, and the same cubic volume scaling, and the same differential galactic rotation. Its tools would be vastly more sophisticated than ours. Its energy systems would be incomparably more efficient. Its institutional structures might endure for timescales we cannot imagine, but it would still fragment at some horizon. That horizon might be larger than ours, perhaps significantly larger, but it would still be finite, and it would still be vanishingly small compared to the 100,000 light-year diameter of the galaxy it inhabited. The Milky Way is not empty as civilizations destroy themselves in nuclear wars where artificial intelligence catastrophes or recreational. Those scenarios may or may not occur, but they are not necessary to explain galactic silence. The galaxy is quiet because it is too large, too old, and too entropic for any single organizing intelligence to hold together across its full extent. The speed of light ensures that information arrives too late to coordinate action. The energy economics of interstellar travel ensure that expansion decelerates and stalls long before reaching galactic scales. The thermodynamics of entropy ensure that every structure, every colony, every network node fights a losing war against decay that eventually claims everything not continuously sustained by local energy inputs. And the timescales of galactic evolution ensure that the playing field itself transforms faster than any civilization can adapt its network to match. What remains is not a galaxy devoid of life or intelligence. What remains is a galaxy where life and intelligence arise in scattered localities, build outward to the limits physics permits, and then persist as isolated islands in an ocean of space, too vast and too old for any bridge to span permanently. Local civilizations may burn brightly for millions of years. They may achieve wonders we cannot currently conceive, orbital habitats, terraforming worlds, stellar engineering, perhaps even feats of physics we have not yet discovered. But they will achieve those wonders locally, within their fragmentation horizons, within the volumes of space where the speed of light permits coordination, where energy budgets permit maintenance, and where entropy can be held at bay through continuous, sustainable effort. The galaxy does not punish ambition. It simply forces limits. Those limits are written in the equations of relativity, thermodynamics, and quantum mechanics. The same equations that permit stars to burn, planets to form, and life to emerge in the first place. The physics that creates the possibility of intelligence is the same physics that constrains its spread. The universe gives rise to minds capable of dreaming about galactic empires, and quietly ensures that those empires can never cohere across the distances it provides. This is not tragedy, it is structure. The Milky Way is not a territory to be conquered. It is an archipelago of possibility, where each island of intelligence lights its own small fire against the darkness, visible only to its nearest neighbours, invisible to the rest. The silence between the stars is not empty. It is full of physics, doing exactly what physics has always done, shaping what is possible, and gently but absolutely forbidding what is not. And perhaps there is something unexpectedly beautiful in this conclusion. Humanity has spent centuries dreaming of galactic empires, vast civilizations commanding millions of star systems, their fleets crossing the spiral arms, their authority spanning the disk from core to rim. Those dreams are magnificent. They speak to something deep in the human desire to explore, to grow, to leave a mark on the cosmos that outlasts any individual life. But the universe is offering us a different vision. Not empire, not conquest, not a galaxy brought under a single banner. Instead, a galaxy that blooms with countless independent fires, each one a unique expression of intelligence shaped by the particular conditions of its own small corner of the cosmos, each one solving the puzzle of existence in its own way, each one burning with its own light, asking its own questions, building its own wonders, completely unaware of the thousands of other fires burning in other distant corners of the same vast galaxy. This is not a lesser outcome, it is a richer one. A galaxy ruled by a single civilization would be a galaxy of conformity, one set of values, one technological paradigm, one cultural perspective imposed across 100 billion star systems. A galaxy of isolated clusters is a galaxy of diversity on a scale that defies comprehension. Every cluster, an independent experiment in what intelligence can become. Every pocket of civilization a unique answer to the question of how life organizes itself given energy, matter, and time. The galaxy is not diminished by the absence of empire. It is enriched by the presence of countless independent minds, each one a sovereign expression of what the universe can produce when physics permits complexity to emerge from chaos. We are one such fire, burning in the Orion spur of a mid-sized spiral galaxy, surrounded by distances we may never cross, silences we may never break, and timescales that dwarf everything we have ever built or imagined. The galaxy will not yield to our ambition. It will not shrink to fit our reach. It will remain vast, ancient, mostly empty, and structurally resistant to the coherent spread of any single intelligence across its full magnificent extent. But here, in our small corner, we burn. We ask questions. We build telescopes and point them at the darkness. We listen for signals we never receive. And we begin, slowly, to understand the architecture of the universe that made us. An architecture that creates islands of light in an ocean of distance, and trusts each island to illuminate its own small patch of the infinite dark.
Of all the objects in the cosmos, none are as strange, mysterious, or powerful as black holes.
Black holes are the most mind-blowing things in the universe.
They could swallow a star completely. Black holes have these powerful jets that just spew matter out. First discovered on paper, on the back of an envelope, some squiggles of a pen. The bizarre solution to a seemingly unsolvable equation, a mathematical enigma. Einstein himself could not accept black holes as real.
People didn't even believe for many years that they existed.
Nature doesn't work that way. Yet slowly, as scientists investigate black holes, by observing the effect they have on their surroundings, evidence begins to mount. That is the proof of a black hole.
Millions of times the mass of the sun.
Cutting-edge discoveries show
We did it.
black holes are very real.
I thought it was crazy. I said, holy.
But what exactly are they? If we could visit one, what might we see? With their immense power, do black holes somehow shape the very structure of the universe? Is it possible we might not exist without them?
It's quite a journey.
Black hole apocalypse. Right now on Nova. There are apocalyptic objects in the universe, engines of destruction, menacing and mysterious. Black holes. Even scientists who study them find them astonishing. Black holes can sort of blow your mind.
I'm amazed that these objects actually exist.
Black holes defy our understanding of nature.
Black holes are the greatest mystery in the universe.
They're completely invisible, yet powerful beyond imagining. They can tear a star to shreds.
Black holes actually will eat anything that comes in their path.
You really want to avoid them at all costs.
Black holes even slow time. Once thought too strange to be real, black holes shatter our very understanding of physics. But we're learning they may somehow be necessary for the universe we know to exist.
They might well be the key players in the universe.
What are these strange, powerful objects? Outrageous and surprising. Where are they, and how do they control the universe? The search for black holes is on, and it will be a wild ride across the cosmos to places where everything you think you know is challenged, where space and time, even reality, are stranger than fiction. And we're starting that journey at a very unlikely place. Here, at a remote location in Washington State, where for the first time, a radical new experiment has detected black holes. It originated over 50 years ago, when a few visionary scientists imagined a technology that hasn't yet been invented. searching for something no one is certain can be found. The experiment is daring and risky. Failure could mark their lives forever. But they don't fail. Right here in these facilities, they make a remarkable discovery. In the early hours of September 14th, 2015, they record a message. It looks and sounds like this. Just a little chirp. But that chirp is epic, monumental. The signal traveled over 1 billion light years to reach us. It started far, far away. And what it tells us is this. Somewhere in the cosmos, over 1 billion years ago, two massive black holes circle each other in a fatal encounter. Closer and closer they come, swirling faster and faster, until finally they slam together. The black holes create waves that spread outward, just like vibrations on a drum, or ringing in the fabric of space itself. The collision creates a massive blast, putting out 50 times as much power as the entire visible universe. It sends out a wave not of heat or light or sound, but of gravity.
This gravity wave is moving its way through the universe at the speed of light.
The wave races by stars. On the young Earth, supercontinents are forming. Microscopic organisms have just appeared.
Washing over one galaxy after another, after another.
Dinosaurs roam the Earth.
The wave is still moving.
It zooms through clouds of dust.
And then it nears the Milky Way galaxy.
The Ice Age is just beginning.
We're troglodytes, drawing in caves.
The wave reaches nearby stars. Albert Einstein is in the 6th grade. The wave approaches as close as Alpha Centauri. At midnight on September 13th, 2015, it is as close as Saturn. Finally, over 1 billion years after the black holes collide, the wave reaches us. It strikes a pair of revolutionary observatories, the sites of the daring experiment. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. The experiment, 50 years in the making, has finally hit the jackpot and opened an entirely new way of exploring the universe. For 400 years, almost everything we've observed in space has come to us in some form of electromagnetic energy. That little chirp is different. What hits the Earth in September 2015 is a gravitational wave, a squeezing and stretching of the very fabric of space. It produced no light. No telescope could ever see the collision. We needed an entirely new kind of observatory to detect it. That wave is new and direct evidence of one of the strangest mysteries in our universe, black holes. Most of us have heard of black holes. They're invisible, powerful. We're talking about things that are 1 billion times the mass of the sun. Bizarre. A physical entity with infinite density. No beginning, no end. They pull things in and warp light. Approach one, and time itself begins to change. Gravity is so intense that a moving clock will tick slow.
Time will become so slow that you will watch the entire future of the universe unfold before your very eyes.
fall in and you'd be squeezed as thin as a noodle.
You'll be extruded through the fabric of space and time, like toothpaste through a tube.
Today, we know more about black holes than ever before. But the more we learn, the more mysterious they become.
They're the most exotic objects in the universe. We don't have the physics to describe them.
No matter how well you understand them, they remain unreachable in some sense.
Now, gravity's greatest man is about to enter the black hole.
So black holes have a pretty fierce gravity. And if you want a villain for a sci-fi movie, cast a black hole. But in reality, what exactly is a black hole? And where do they come from? You might think a black hole is like this. An object, but it's not. It's a hole in the fabric of space. A place where there is nothing except gravity. Gravity at its most intense and overwhelming. So black holes are all about gravity. Gravity at its most extreme. What exactly is gravity? We're all familiar with gravity. It rules our lives. But even so, for a very long time, how gravity actually works was one of the greatest mysteries. Over 300 years ago, Isaac Newton was fascinated with the behavior of moving objects. Eventually, he figured out his laws of motion. They work so well, we still use them today. But Newton's laws can only describe gravity's effects, not explain what it is. And here's where Albert Einstein comes in. Like Newton, he thinks about objects in motion. And he wonders what gravity actually is. Is it a force, or could it be something else? Here's what concerns Einstein. Take this apple. I can't move it without touching it. But if I drop the apple, it moves toward the earth. What if I take my hand away? And the floor, and the basement, the floor and all that, then what? The apple just keeps falling. Einstein realized that gravity has something to do with falling. Now, if I throw the apple, it falls along a curved path. But imagine I could get the apple moving much faster. Eventually, if I get the apple moving really, really fast, say 17,000 miles an hour, its curved path matches the curve of the Earth. The apple is in orbit, falling freely, just like the International Space Station and the astronauts inside it. According to Einstein, the apple and the space station and the astronauts are all falling freely along a curved path in space. And what makes that path curve? The mass of the Earth.
Einstein came up with a supremely simple concept, and that is space-time is dead. The Earth runs all the objects in the world.
So according to Einstein, the mass of every object causes the space around it to curve.
And that was Einstein's conception. There are no forces anymore. There's just objects bending space-time and other objects following the straightest line through it.
All objects in motion follow the curves in space. So how does the Earth move the apple without touching it? The Earth curves space, and the apple falls freely along those curves. That, according to Einstein's general theory of relativity, is gravity, curved space. And that understanding of gravity, that an object causes the space around it to curve, leads directly to black holes. But it's not Albert Einstein who first makes the connection between gravity and black holes. It's another scientist.
Karl Schwarzschild was a German astronomer, head of the Potsdam Observatory in Germany.
Ever since he was a teenager, he'd been calculating complicated features of planetary orbits.
As Einstein unveils his theory of gravity in 1915, Karl Schwarzschild is in the German army, calculating artillery trajectories in World War I.
And just weeks after Einstein presented his papers, Schwarzschild, then on the Russian front, quickly got a copy and was mapping the gravitational field around a star.
Einstein had gotten at it through a series of approximations, but Schwarzschild, sitting on the front with bullets and bombs flying, calculated an exact solution to Einstein's theory and sent it to Einstein. Einstein was astonished. He hadn't even imagined that you could solve these equations exactly.
But Schwarzschild isn't done. In his solution to Einstein's equations, he discovers something Einstein himself had not anticipated.
Schwarzschild said, I can calculate this strange distance from a gravitating object that represents a kind of a boundary.
Schwarzschild mathematically concentrates a mass, for example, a star, into a single point. Then he calculates how that mass would bend space and curve rays of light passing nearby.
As he, through his mathematics, aimed particles of lighter matter towards this point, there was this boundary surrounding the point at which the particles would just stop. The particles disappeared. Time stopped.
Schwarzschild has discovered that a concentration of mass will warp space to such an extreme that it creates a region of no return. Anything that enters that region will be trapped, unable to escape, even light.
It's like those Russian hotels. You can check in, but you can't check out. Once you go across that boundary, even if you can sail through, there's nothing you can do to get out. There's nothing you can do to signal out. It becomes this strange cut-off portion of space-time.
What Karl Schwarzschild has discovered is that any mass compressed into a small enough space creates what we today call a black hole. But Albert Einstein, whose own theory of gravity predicts such a thing, cannot believe it can happen in the real world.
Einstein didn't think that nature would act like this.
He didn't like this idea.
Karl Schwarzschild becomes ill and dies before he has a chance to further investigate his own discovery. 2.5 years later, in November 1918, World War I ends. The strange theoretical sphere discovered by Karl Schwarzschild seems destined to be forgotten. Nothing but a curious historical footnote. But in the coming decades, physicists learn more about the atom and about how fusing atoms powers stars, a process called nuclear fusion. Some begin to wonder if something like a black hole can actually come from a star. But not just any star. It would have to be big.
Stars are born in litters, and you get a distribution of sizes and masses. Thousands of little stars, and a few big stars, very big stars, incredibly massive. Stars are in many ways similar to living creatures.
Like humans, they have life cycles. Investigating stars' life cycles in the 1930s, two visionaries, Subramanian Chandrasekhar and Robert Oppenheimer, discovered that the most massive stars end their lives very differently from smaller ones. The life cycle of a star really depends on its mass. The mass of the star determines what's going to happen after it finishes burning its hydrogen. All stars start out burning hydrogen, the lightest atom, using hydrogen atoms into helium, working their way up to heavier elements. Gravity wants to crush the entire mass of the star, but the enormous energy released by fusion pushes outward, preventing the star from collapsing. Stars are stable because we have an outward-moving pressure due to nuclear fusion, and that's balancing with the inward force of gravity. Smaller stars can't fuse elements heavier than helium. But in the most massive stars, fusion crushes heavier and heavier atoms, all the way up to iron.
Iron is such a massive element, it has so many protons in it, that by the time you fuse iron, you don't get any energy back out.
Iron is a dead end for stars. Fusing atoms larger than iron doesn't release enough energy to support the star. And without enough energy from fusion keeping the star inflated, there's nothing to fight gravity.
And gravity wins. So the entire star collapses.
Very rapidly, trillions of tons of material come crashing down, hit the dense core, and bounce back out, right off the outer layers of the star in a massive explosion. A supernova. The more mass, the more gravity. So if the remaining core is massive enough, gravity becomes unstoppable.
There's an unknown force to prevent the collapse. So it is a testimony of small
Gravity crushes the stellar core down smaller and smaller and smaller until all its mass is compressed in an infinitely small point. A black hole. The theory makes sense, but most physicists remain skeptical about black holes.
Einstein and Eddington, all the sort of preeminent astrophysicists from the 1930s to 1950s, did not believe that they were actually real. It remained a solution, a mathematical enigma for a very long time. So it took a long time for people to even start looking for them.
It's not until the 1960s that the idea of a supernova creating a black hole is taken seriously. Princeton physicist John Wheeler, who had originally been a skeptic, begins to use a name from history for these invisible objects. Black hole.
The term black hole originates in India. The black hole was the name of an infamous prison in Lahore.
Still, no one has ever detected any sign of a black hole. And in 1967, graduate student Jocelyn Bell discovers a strange, extremely tiny, dead star that gives off very little light. A neutron star. The cold remains of the stellar collapse. The neutron star gives astronomers more confidence that black holes, much heavier dead stars, might also exist. A half century after Carl Schwarzschild mathematically showed that black holes are theoretically possible, scientists have identified the natural process that might create them, the death of large stars.
So these giant supernova explosions of extremely massive stars make black holes.
Any star that is born with a mass that's about 10 times the mass of the sun or higher will end in a black hole. So our galaxy is replete with little black holes, which are the stellar corpses of generations of stars that have come and gone.
So what are these invisible stellar corpses like? Imagine I'm exploring space with some advanced technology for interstellar travel so that we could visit a black hole, maybe one in our own galactic neighborhood. This particular black hole isn't very big, only about 10 solar masses, meaning 10 times the mass of the sun. And like all black holes, it has an event horizon. A distinct edge to the darkness. That's the boundary Carl Schwarzschild first discovered. The gravity is so strong that nothing can escape, not even light. And that's where we're going. As we get closer, some very strange things begin to happen. Look at the edge of the black hole. See how the image of distant stars is distorted and smeared into a circle? That's gravitational lensing. The black hole's extreme gravity bends the path of light passing by, so that a single point of light, like a star, briefly appears as a ring around the event horizon. I'm now deep in the black hole's gravity belt, and we're going to start experiencing the effects. The extreme gravity actually slows down time relative to the Earth. From their point of view, I appear to be slow. But from my point of view, time on Earth is speeding up. Now let's say I want to get even closer by taking the space. The way the black hole slows down time is about to get even more pronounced.
Tracking the changes I'm about to experience, I'm turning on the zero getting within 1 second. For years, each shadow of the event horizon approaches, and my light blinking normally. But watching from shift, the closer I move towards the black hole, the more slowly I appear to move. The pulses are nearly infinitely spaced. So it looks as though I'm frozen in time. For me, every day is completely normal, even when I reach the event horizon. If you waited long enough, maybe millions or billions of years, a ship would finally see me disappear. And that's the last we see of me. What's inside a black hole? That's still a mystery. And even if I find out, I can never go back and tell you. But I can say this. Black holes may be dark from the outside, but inside they can be bright. I can watch the light from the galaxy that's falling in behind me. And that's the last thing I'll ever see. Unfortunately, the fun is about to end. Now that I've crossed the event horizon, I've fallen towards the center, where all of the mass of the black hole is concentrated. And I'm beginning to get stretched. As I fall in, the gravitational pull at my feet is stronger than at my head, and my body is starting to get pulled apart. I'll be stretched as long and thin as I do, spaghettified, and ultimately I'll end up completely disintegrating into my fundamental particles, which are then crushed to infinitely small points.
A singularity, where everything we understand about space and time breaks down. A black hole, less than 40 miles from the outside, is as big as a universe on the inside. And as I pass through, my particles will join the primordial soup of a new beginning. So that's what theory tells us we might experience if we could travel to a black hole. But how can you know for sure? How can you investigate something you can't even see?
There are ways to investigate if something is happening somewhere, even if I can't see that thing directly. Take Yankee Stadium. What's happening inside there? Is there a game going on? I can't see the field. I can't see any players or baseballs or bats, but I can definitely tell if there's activity around the park.
It's pretty clear something is going on. It might seem obvious, but whatever it is, I can learn a lot just by observing the happenings around the stadium.
And these do look a lot like baseball bats. And that's the way we investigate black holes, by observing the effect they have on their surroundings.
But what sort of effects? How might a black hole reveal itself? Starting just before World War II, two monumental discoveries are about to radically change astronomy. In 1931, Bell Labs engineer Carl Jansky picks up mysterious radio waves emanating from deep space. Then the sky gets even stranger. When scientists mount Geiger counters on captured German rockets and discover the cosmos is also full of X-rays. These discoveries give astronomers important new tools that will revolutionize the hunt for black holes and dramatically expand our vision.
What our eyes can perceive is a very narrow part of the electromagnetic spectrum.
If the electromagnetic spectrum were laid out along the Brooklyn Bridge, the portion we can see with our eyes would be just a few feet wide. Electromagnetic radiation includes waves of many different frequencies: radio waves, microwaves, infrared and ultraviolet light, X-rays, and gamma rays. Radio and X-ray astronomy open up the sky, revealing dim or even invisible objects, blasting out powerful energy no one knew was there.
They began to realize that this very placid thing that we see out there, all this very quiet thing that looks like nothing is happening and the only thing that's moving is the planets, found out that there was madness going on. There was chaos out there.
X-rays come from the high energy end of the spectrum. What is creating all this energy? This much is certain. Whatever the source, it is invisible to ordinary telescopes, and it is hot.
X-rays come from things which are at temperatures of millions of degrees, even tens of millions.
One of the first of these X-ray sources to catch the attention of astronomers is named Cygnus X1.
Cygnus, it was in the constellation Cygnus. X, it was an X-ray source. 1 was the first one he found.
In 1970, Paul Merton is a young English astronomer trying to secure his next job.
I was a research fellow. I was coming to the end of my 2-year contract. And I thought, what can I contribute to find out what these things are?
Merton works in a 15th century castle surrounded by telescopes, the Royal Observatory. Using the largest telescope in England, he begins searching the area of the constellation Cygnus, the Swan. He decides to hunt for pairs of stars. Pairs of stars are called binaries, They may sound exotic, but they're not at all uncommon. Many of the stars we see, perhaps half, are actually binaries, pairs of orbiting stars locked together by gravity. But Merton wondered, is it possible there are binaries where only one of the stars is visible?
They thought that maybe there was a kind of a star system in which one ordinary star made light, there was another star nearby that made X-rays.
The telltale sign of the binary is that the stars are moving around each other. So Merton begins searching for a visible star that shows signs of motion. When the star is moving toward us, it appears more blue as the wavelength of its light gets shorter. Moving away, it appears more red as the wavelength of its light gets longer. This is known as Doppler shift. After looking for color changes in hundreds of stars in the area of Cygnus, Merton spots a possible suspect, a visible star whose light is shifting as though moving around.
A double star. The star was moving around and around, going around once every 5.6 days.
But whatever it's going around can't be seen.
There was no trace in space of the second star. There was one star there, there was a second star there.
Merton has a binary pair in which only one star is visible. The second object emits X-rays, has enough mass and gravity to dramatically move the star, but gives off veiled light. Could it be the corpse of a star massive enough to become a black hole?
The crucial issue in deciding whether Cygnus X1 was a black hole was to measure the mass of the X-ray emitting object.
It would have to be very massive, at least 3 times the mass of our sun. If not, it's probably just a neutral star. A black star that's dense, but not heavy enough to be a black hole.
So the observers needed to come up with a conclusion that the dark object, the X-ray emitting object in Cygnus X1, was heavier, hopefully substantially heavier than 3 solar masses.
From these observations, Merton is able to make an estimate of the mass of the invisible particle.
And the answer came out to be 6 times the mass of the sun. So there was a story then that Cygnus X1 was a black hole. And the key to it was that the mass of the star we couldn't see was more than 3 solar masses. When I finished writing it, it's a black hole.
This would be the first actual detection of a black hole. It's a huge claim, and Merton will have to convince skeptics, starting with his boss.
The Astronomer Royal, Sir Richard Woolley, he didn't really go for black holes. It's all fanciful. A lot of people in California are talking about this. There are a lot of funny people in California, you know, a lot of hippie type people.
People like theorist Kip Thorne.
So I was nervous about it. I was nervous about the scale of the discovery, and actually so were other people all around me. I was working with a fellow scientist, Louise Webster, and we were modest about the claim that we were making because we knew what people would think of it. And if you look at the paper we published, it just mentions the word black hole once, right at the end. We think this might be a black hole.
The Paul Merton Louise Webster paper appears in September 1971. Other astronomers agree it could be a black hole, but no one knows for sure. 3 years later, Kip Thorne and the noted British physicist Stephen Hawking make a now famous wager about Cygnus X1.
We made a bet as to whether Cygnus X1 really was a black hole or not.
The bet is partly in jest. Both men hope it is a black hole. But Hawking, not wanting to jinx it, bets against his own wishes.
Stephen claims that Cygnus X1 is not a black hole, and I claim it is a black hole. So we signed that bet in December 1974. And gradually, the case that it really was a black hole became stronger and stronger and stronger. So in June of 1990, Stephen broke into my office and he thumbprinted off on the spec and sealed it out in my absence. I came back from Russia and discovered it being concealed.
Now by 1990, the evidence of Cygnus X1's mass may be strong enough to settle a bet between two friends.
But the original estimate wasn't precise enough to be definitive.
In order to calculate mass, Paul Murden had to rely on rough estimates of the distance to Cygnus X1, which varied by a factor of 10.
And the question wouldn't be answered for another 20 years, until astronomer Mark Reed became intrigued by the puzzle.
Reed is an astronomer at the Harvard-Smithsonian Center for Astrophysics when he sets out to conclusively prove that Cygnus X1 is a black hole by measuring its precise mass.
But how can you measure the mass of an invisible object? Using laws developed by German astronomer Johannes Kepler in the 1600s, it's possible to calculate the mass of a celestial object, but only if you know its distance.
Distance in astronomy is absolutely fundamental. If you don't know distance, you don't know what the object is. It could be a very nearby firefly-like thing. It could be a very distant, huge star, much, much bigger than the sun.
So to get the true, precise mass of Cygnus X1 and confirm that it is a black hole, Reed needs to know how far away it is. But how can he measure the distance to a star? The secret lies in a familiar phenomenon, parallax. It's what our eyes and brains use to see in 3 dimensions.
You can put your finger up at arm's length, look at it, and close one eye, this is my left eye, and I'm looking at my finger relative to the wall in the background there. Now if I open my eye and close my right eye, I see my finger has appeared to move with respect to the original position. And that's because our eyes are separated and we view from different vantage points.
To use parallax to measure distance to an object in the sky, astronomers let the motion of the Earth provide the 2 different vantage points.
Imagine Cygnus X1 is right here, and the Earth and the Sun are over there. Now, the Earth goes around the Sun once a year. And in the springtime, the Earth ends up on one side of the Sun, and we observe Cygnus X1 along a ray path like this. And 6 months later, the Earth goes around the Sun to the other side. We get a different vantage point from Cygnus X1.
Now he has a triangle that goes between the Earth and its 2 positions and Cygnus X1. We know the base of the triangle, the diameter of Earth's orbit. And the principles of geometry tell us that all we need to calculate the distance is the size of the angle at the top.
And we measure this very small angle here at the point at Cygnus X1. And then from direct geometry, we can calculate the distance to Cygnus X1, and from that infer a very accurate mass.
The concept is simple, but Cygnus X1 is so far away that the angle to be measured is minuscule, a tiny fraction of 1 degree. It's smaller than the angle spanned by Abraham Lincoln's nose on a penny in San Francisco, viewed from New York. Because the angle is so very tiny, it can't be measured by any one telescope. But Reed's team has a solution.
We take 10 radio telescopes, go across the continental US and to Hawaii and to St. Croix in the Virgin Islands. We use these telescopes simultaneously, and we synthesized in a computer. The telescope has a diameter the size of the Earth. That gives you incredible angular resolution.
Using this technique, Reed's team determines that Cygnus X1 is 6,000 light years away.
With the new distance we got, 6,000 light year distance, we were able to determine that the mass is about 15 solar masses, easily realized.
40 years after it was identified as a possibility, Cygnus X1 is now widely accepted as the first confirmed black hole.
It's an unexpected finding, and the fact that Molly May was on it and Louise Webster's was on it did us a lot of good in our careers. I think as a result of this discovery, I got offered a permanent job. It was a great celebration for the family. So it worked out very well for me, as well as getting the intellectual satisfaction of solving a problem.
So finally, after years of speculation, we have a real black hole. Not only that, but a black hole that's blasting out X-rays and has a companion star. If we could visit in my imaginary spaceship, what would we see? The distance to Cygnus X1 has been established at 6,000 light years from Earth. And its mass is 15 solar masses, or 15 times the mass of the Sun. And Cygnus X1 is surrounded by an accretion disk, a disc-shaped cloud of gas and dust outside its event horizon, the point of no return. As gravity pulls matter toward the black hole, the cloud starts rotating, just like water being pulled down a drain. Within that accretion disk, particles closest to the black hole whip around at half the speed of light. It's like a giant particle accelerator in space. But why does it emit X-rays? As those particles race around, they collide, which heats them up to millions of degrees. When they get that hot, particles blast out X-rays. And it's those X-rays that first led astronomer Paul Merton to investigate this black hole nearly 5 decades ago. And there's something else about Cygnus that's different. It has a companion star. This blue supergiant star orbits the black hole once every 5.6 days. It orbits so close to Cygnus X1 that the black hole strips material off the star and pulls it into the accretion disk. Some of that material will cross the event horizon and get swallowed up. But not all of it.
Some of the stuff actually comes back out before ever entering the black hole. Kind of like a toddler eating. Half the pasta ends up on the floor, half of it maybe on the ceiling, and some of it in the mouth.
One of the most striking and enigmatic features of Cygnus X1 is its enormous jets. These beams, particles, and radiation stream outward from Cygnus's north and south poles, perpendicular to the accretion disk. There's still a lot we don't know about these jets, but they are tightly focused and extremely powerful, blasting out at nearly the speed of light and extending well beyond Cygnus.
When gas gets to these high temperatures and produces the light, there's also a magnetic field that forms around them. And we don't understand exactly how, but these magnetic fields help pollinate these massive outflows from black holes. Powerful hoses, if you will, that just spew matter out.
So that's Cygnus X1, if we could see it up close. A growing, feeding black hole with huge jets, blasting particles way out into the universe. They're almost these breathing, fire-eating demons. They flicker and burst. It's a very violent fireball, very quick. mathematical curiosity has now become quite real. After decades of skepticism, scientists now accept that burned out corpses of large stars can trap light inside them, warp space and time around them, attract matter, and accelerate it to mind-boggling speeds.
Black holes seem like such a radical idea that we should accept it. But bit by bit, the evidence for black holes has gotten stronger and stronger, and we've seen these amazing things.
At least 20 black holes have been found in our galaxy. X-ray binaries like Cygnus X1. And there are probably millions more of these massive stellar corpses in our galaxy alone. Still, a stunning surprise awaits. Everything astronomers think they know about black holes, and much of what they believe about the universe itself, will be upended by a shocking discovery. The revelations begin when radio telescope surveys of the sky detect mysterious hotspots emitting radio energy.
They were coming from what looked like stars.
Because these objects resemble stars, but were discovered through radio signals, astronomers name them quasi-stellar radio sources, quasars. But are they stars or not? The first step in investigating them is to figure out what they're made of. To do that, astronomers analyze the electromagnetic energy they emit. Every element has a unique spectral fingerprint. For example, carbon, helium, hydrogen. These lines reveal the chemical makeup of a star. But the spectrum of a quasar turns out to be incomprehensible.
They looked at it and it was gibberish. It didn't look like there were any emissions from elements that they knew.
What are they missing? There has to be a clue somewhere. Finally, in 1963, Caltech astronomer Martin Schmidt finds it, hiding in plain sight. Buried in the quasar spectrum is the fingerprint of hydrogen.
I noticed something familiar, but it was in the wrong place. The fingerprints of hydrogen had been shifted way off to the ring.
It was hard to spot because the spectral lines of hydrogen were radically shifted toward the lower frequency end of the spectrum. And that could only mean one thing. The quasar is moving away from us at fantastic speed. But astronomers have almost never before seen light shifted to such an extreme. Like a familiar sound shifting too low to understand. The light from quasars has shifted to such a degree that hydrogen is unrecognizable. This extreme amount of shift means quasars are racing away from us at blinding speed. The reason? It's the legacy of an event that occurred almost 14 billion years ago. The Big Bang. The beginning of our universe. Ever since, the universe has been expanding, carrying with it all the objects it contains, quasars.
Almost no one had ever seen anything moving away at that time. This made this object almost the furthest away thing that had ever been seen, which meant the thing itself had to be so luminous, and you had to account for that.
2 billion light years away, putting out the energy of 1 trillion suns per second. Possibly create that.
No one had any idea what could be powering these things. Where could all of this energy come from?
If you work out through calculations again, chemical energy, it couldn't be nuclear energy.
There's no way a quasar can be a star. No amount of nuclear fusion could produce that much star power.
only engine that could possibly put out that much energy is gravity.
Gravity. In everyday life, we can overcome gravity easily. But when concentrated to an extreme by a black hole, gravity is overwhelmingly powerful. A handful of scientists start wondering, could quasars perhaps be powered by gravity engines? What if the energy blasting out from quasars is coming from bright accretion disks around black holes?
To produce that kind of energy, that kind of brightness, it has to involve a black hole.
But not just any black hole.
Whatever was the source of the emission from a quasar had to be massive. How massive? Well, millions or billions times heavier than the sun.
Millions or billions of times heavier than the sun. Cygnus X1 is only 15 times the mass of the sun. The black holes powering quasars are an entirely different category of black holes. Supermassive. And they seem to be located in the centers of galaxies. But what about our own galaxy? Could there be any supermassive black holes closer to the Sun? The center where any supermassive can be found lies in the direction of the constellation Sagittarius, the Archer. Now, Sagittarius isn't just any constellation. It's in the direction of the center of the whole Milky Way galaxy. But since we live inside the Milky Way, we can't see the galaxy the way the spacecraft would. But I can use my trusted imaginary star machine to show us the galaxy from the outside. Our home is a spiral galaxy, hundreds of billions of stars drawn together into a gigantic disk. It's wide, about 100,000 light years across, but it's relatively thin, only about 1,000 light years. And the whole spiral slowly rotates. Our solar system is here, and here, 26,000 light years is the center, which we see in the direction of Sagittarius. In this dense center, there are millions of stars, lots and lots of dust and gas. So that's the view of our galaxy from the outside, thanks to our imaginary technology. But since we live inside the Milky Way, when we look towards the center, we're looking through much of our own galaxy, which means it appears to us as a band of stars and dust across the sky. Our Milky Way. Deep inside this band of stars and dust, a supermassive black hole be lurking. In the 1990s, astronomers grow determined to solve the mystery, to peer through the murky Milky Way and learn what, if anything, is at its center. One of them is Andrea Ghez. Ghez takes on a daunting challenge. She will try to track individual stars orbiting the center of the galaxy.
The essence of this experiment comes from watching stars orbit the center of the galaxy. So you want to find the star as close to the center of the galaxy as possible. Which means that I want to get access to the largest telescope I can possibly get my hands on.
And that means Summit of Mauna Kea, a dormant volcano almost 14,000 feet above the beaches of Hawaii. High altitude and humidity make this the ideal place for astronomy. The instrument Ghez uses is Mauna Kea's Keck Observatory, one of the largest in the world. But despite its size, Keck has the same problem as all telescopes on Earth: atmospheric distortion.
Think about looking at a pebble at the bottom of a river.
The river
Hmm. 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 you Good mornings. Hello, buddies.
So I just want to reply to this guy here, right? So here we go. I need some motivation this morning, so let's check it out, right? So let's start this guy. Let's try how it goes.
Good mornings, my friends. Oh my! What's going on here? Oh my goodness, what a pickle! Oh my! Oh goodness. I hope everyone's doing okay. It's always difficult when I wake up. I'm always very shaky. Yeah, this is true. Very, very shaky and nervous. I'm going, yes. Oh, mine is. I know I'm shaky and nervous, so let's have a coffee. Oh, that's a good idea, isn't it? I don't know. It's very difficult sometimes. Yes. Don't worry, I'm just acting this. That's very upsetting, you know. We would say I'm acting this. It's not very nice, really. My struggles are real, when you think about it. Coffee. Coffee. Hello, buddy. How are you doing? Hello, Ellie.
He needed you. And what did you do? After all these years, he gave you his heart.
My ears are ringing so loud, so loud. Yes, when you think about it, yes. Yes, when you think about it, yes. Good mornings. I had non-stop nightmares. Non-stop nightmares. They were really bad. They were really bad. Yes. Good mornings. Yes, when you think about it, yes. I don't know. Mm. 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 I don't know. Mm. Mm. The nightmares were just being not taken seriously again. Mm. My brother and mother, we went along to a Deep Mind event, like a conference thing, and you could bring family members. So I brought my mother and my oldest brother, and they weren't listening to anything I was telling them. And they made a big scene in front of everyone and all of my colleagues. And they made a big scene, and it was really embarrassing. It was really embarrassing because they wouldn't listen to me. They weren't taking anything I was saying seriously about Deep Mind or work. They weren't taking anything seriously. And they made a big scene in front of everyone. They looked really stupid. They weren't listening to me. They weren't listening to me. They never listened to me. They never listened to me. Even when I'm talking to them about Deep Mind, say we just released a big paper, research paper, and it's going to go into the Nature Journal, right? So releasing a big paper, and they ask me what the research is all about, and I'm telling them, and they don't listen to me. It's like, I was part of the fucking research. How can you not? I'm telling you what it's about. I was part of it. There's my fucking name there in the co-author. There's my fucking name there in the fucking Nature Journal. That's my fucking name there as a co-author. And you're not fucking listening to me about what it's about. You know? They were doing stuff like that. They won't listen to me. They won't listen to me. They won't listen to me. There's my fucking name in there. You're not listening to me. You know what I mean? Just, you're not listening to me. Not listening to me. Not listening. Not taking in what I'm saying. There's my fucking name in there. That's my fucking name. And you're not listening to me. You know what I mean? Yeah, so it was like that. And it's horrible. Not being listened to. Not being listened to. It's terrible. It's terrible. Yes, that's what I say. It's terrible. Late night cheese. Yeah, buddy. I have nightmares every night. Every night I have nightmares. Every night I have nightmares. And I hate it. Oh shit. My jaw's going a lot. That's why I hate going to bed, because I hate getting up in the morning. I hate it so much. I hate it so much when you think about it. Yes. No, I'll be okay. Can you see my jaw? You probably can't see my jaw, can you? It's going quite a bit. Yes. When you think about it. Where's my fucking medication? What? Where is it? Where the fuck is it? There it is. For fuck's sake. You can't see what? Oh, you can't see it now. It's too much sometimes. It's really too much, you know. It's really too much. People don't think, you know, it's very upsetting when people think I'm faking it. That's not very nice. What? Well, they don't really think I'm faking it. They just want an excuse to hate on me. It's very, very hard what I'm trying to do. Like trying to make a thing on social media and stuff. It's not easy, buddy. It's not easy because people try to stifle you. People try and stifle you, you know? Because they're unhappy. They try to stifle you. Yes, it's true. It's true. Yes, it is. Yes. It's very cruel. I really think most people inside are cruel, and they don't realize it. Like inside, I think they're deeply cruel, but they don't realize it. Like when the people going on the campaign to stop me, I think they are being evil, but sometimes I think inside they think they're saying to themselves that they're doing a good thing or something when actually they're just being evil. They're just being evil and they can't admit it to themselves. They're in denial. Do you know what I mean? They're in denial about their the failures of their character. Do you know what I mean? Hey, buddy. Yeah. When you think about it, when you think about it, my girl said it's so. When you think about it, you think the same, yeah. Like haunted, yeah, exactly, haunted, exactly. He's going around acting like he's a good person, right? And he's like, I'm trying to raise awareness. I let him on the chat, and the first thing he says, "You're a fucking pedo." What? Do you know what I mean? Do you know what I mean? It's like, but they convince themselves that they're good in some way, but you're not good, mate. You're not good. You're just being a cunt. You're just being a cunt. Do you know what I mean? Hello, buddy. Good mornings. I slept quite well. The horrible thing is, I think when I'm sleeping, I'm just really stressed when I'm sleeping. I'm just really stressed, and I keep on waking up. Yeah. Yeah. Came across yesterday because he's seen a exactly. You should type his name in. Look, is that you call that research? Type their name on TikTok and you'll find out who they are. Really? So that's how you do research, is it? Is that how you do research? Go on TikTok and type in someone's name. Yeah, he thinks he's spreading awareness, but at the same time, I think if he was deep down honest with himself, he kind of knows he's not. They kind of know they're not being good, but they want to, you know? Bless you, Casey. Yeah, exactly. They're just cunts, man. I've blocked the accounts that have all my stuff on it, that have people just doing that hatred and stuff. So I really appreciate when people like find stuff for me and show me like stuff people have been saying, like what fucking Karen has done. So I don't have the fucking energy. I don't have the energy to be going around and fucking. I'm just trying to like fucking survive and like make my own little content and stuff, you know. But it's really helpful. Like that fucking wasn't him, that Karen. What cunt, man? Do you know what I mean? Acting like they're my supporter, and just because I rejected you, okay, I rejected you. So what? Now they're on some fucking campaign. You see the text message of us sucking up. Hey, now I can't listen to what over the rainbow now. What? Really? And now you're like, he's horrible, he's this, or whatever they're saying. I'm going to the police now because he called me a goblin or whatever. Fuck off, you cunts. Fuck off, you fucking pussy. What a pussy. What a pussy. What a pussy. She's so fickle. So fucking fickle. So pathetic. I'm going to the police. I'm going to present a report. He said my name. He said my name. Yeah, I say my name every day, bitch. Fuck you. Fucking cunts. And some twat comes like, beep, 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 beep. What a knob. Do you know what I mean? It's so pathetic. And it's evil. That's the other thing about it. It's evil. It's evil. Trying to stifle me. Do you know what I mean? I'm fighting for my life. And to them, it's a game. They're treating it like it's a fucking game. Trying to stifle my growth and stuff. It's not fucking funny, man. It's not funny at all. It's not funny at all. And they put this little post. I think I uploaded it. Well, they found my other account, obviously, and they're like, "Let's go." You know, sheep, we're coming, or whatever it was, you know, and we come in packs or whatever. You're advertising. You're showing off that you're bullying me. You're showing off that you're bullying me. And you're trying to intimidate me actively. I'm not trying to destroy their accounts. I'm going to get them prosecuted. Yeah, they don't think it's wrong. But I called her out. I called her out. I called her out. I gave her a chance before I blocked her. I called her out with the bad comments. Right? And she carried on. So then I blocked her. And then she shows what I knew. That's what I knew. I said, you're a fucking dickhead. That's why I blocked you. Commenting on their hatred is wrong. Yeah, exactly. She's going along. She's taking part in conspiracy to commit slander. That's what that is. And they're so pathetic. And they're just so pathetic. They're so pathetic. They're so pathetic, but evil as well. Really evil. Really evil. It's actually evil. It's actually evil. And they say in the comments, someone wrote, like, what were you in jail for? Yeah, I said for speaking out against corruption. That's what I was in there for. That's what I was in there. You know, the charges were for not obeying bail conditions or whatever, which were not to speak on social media, right? And that's because they're framing me. And then they, behind my back, they don't reply there. Behind my back, they go, yeah, he said this, but isn't that nonsense? They don't even, do you know what I mean? They're playing a little game. They're playing a game, but it's not a fucking game to me. It's not a game to me. This is my fucking life. This is my fucking life I'm fighting for. And they're like, oh, he called me this. I'm going to the police. And considering his record, that will look really bad, won't it? That's fucked, man. That's fucked. That's fucked. That's trying to throw petrol into the fire. That's fucked. That's fucked. That's evil. That's not just reporting it for its own sake, but it's reporting it to try and make things worse and upon me. That's fucked. Fucking goblin. She is a goblin. She's literally a goblin. Like evil. Evil goblin. Evil goblin. Evil. You know what I mean? I bet that hurts her. So it's not that bad, mate. Call me a goblin. I don't give a fuck. Call me a goblin to my face. I don't give a fuck, mate. I don't give a fuck. Call me a goblin. I don't give a shit. I don't give a shit. Like I'm going to go to the fucking feds. Somebody put my picture online with my real name. Yeah, is this a rejection, mate? Yeah, she's very insecure. Like, my fiance rejected me after 11 years, right? I didn't go on a hate campaign against her. I don't, like, it was very hurtful. But it's hey, what else are you going to do? You know, you've got to leave someone somehow. It's not going to be fun. I'm not going on some fucking campaign to destroy her life. That hurt, right? That hurt really bad. But it is what it is. It is what it is. That was a very hurtful rejection. Like, unbelievably. Like, it's changed me for the rest of my life, right? I'm not going to try and destroy her now. That's her right to do that. That's her right to do that. That's her right to do that. I have to accept it. And I rejected it on social media. I rejected it on social media. That hurts her that bad. What a fragile person. Yes. Very insecure. Turned to hate instantly. Turned to hate. Because there always was the hate there, really. Because you were saying comments that were hateful. Like when I was making jokes, I made a joke about like women, right? And like I uploaded one last night. You fucking bitches! Why did you leave him? You know, that sort of stuff. And I don't think she thought it was a joke. And she said something like, "Yeah, to be fair, women can be cunts" or something like that. I was like, "No, my video was a joke. My video was a joke. Yeah, you know, you're missing the point. You know, it was a joke." So she's not very, you know. I guess she's lesbian or something. And she gets rejected a lot or whatever. I don't know. But my rejection is I'm just some guy on social media who fucking blocked you. I've been blocked. I was on someone's live stream and they blocked me. I was like, okay. They blocked me. That's it. Just move on. You know? Lives on her higher ground. Yeah. Exactly. To try to, you know, butt hurt. Yeah. She's got some moral high ground. Do you know what I mean? No wonder people reject you if you behave like that. I was making a joke. The joke was, in a way, it's like, you know, like the one, I did one yesterday, like, you fucking left her, you bitch. You know, it's just a joke. It's a joke. It's not real. You know, it's like a woman hate joke, right? Like the manosphere kind of thing. You know, I don't mean that shit. I'm trying to bring attention to people like that. I've seen more of that woman, by the way. Were you there yesterday when I showed you that woman? You fucking... Wait, what was it? How's it go again? He fucking loved you. And what happened? Why didn't you just sit down and listen to him? You don't understand what it's like for a man. You know. Karen Stoic, yeah, she wasn't very stoic there, was she? She wasn't very stoic. That's why when I saw stoic, I had to take the mix sometimes because she wasn't acting very stoic, right? Even I was a lot more stoic than her. She's always losing her shit. So that's not stoic, is it? When people call themselves shit like that, it's like, my name's Karen Stoic. It's like, you're not stoic, mate. That's not stoic behavior. Stoic is supposed to be, you know, you can deal with things and you're, you know, you're above it or whatever. But you're always losing your shit. That Christine was there. That was another woman I rejected. You know why I rejected her? Because she was like telling me off. You know how do people like passive aggressively tell you off? They're like, they keep on saying, it's always something like, you're a nice guy, but, or whatever. And then that Christine, I blocked her. I got annoyed. And now it's like, always a pompous twat or whatever. It's like, you guys, how old are you guys? How old are you guys? This is not playground shit. This is my fucking life. And you're making a game out of it. Oh, yeah, shit. I need to restart the stream before it gets too long so it can upload. Sorry, guys. I'll be back in literally just a second. You remember that happening? Were you there, yeah? Well, I'll be back in a second, yeah? Back in a second.